What if the sun itself chose the exact moment an interstellar visitor crossed our skies to twist its vast magnetic field? Within the same week, auroras bled into latitudes that hadn't seen them in centuries. Satellites slipped into emergency modes, and the South Atlantic anomaly fell eerily quiet as proton levels dropped. At the very center of it all, 3I Atlas, the green wanderer from another star, cutting across the ecliptic like a cosmic blade. Forecasters expected routine turbulence, but instead they found models collapsing, data contradicting itself, and a solar cycle suddenly burning far hotter than predicted. Was this a random overlap of storms and visitors, or a glimpse into hidden connections between the Sun, Earth, and the galaxy itself? Stay with me until the end, because tonight we'll unravel the mysteries behind this magnetic twist and what it could mean for the future of Solar Cycle 25 and beyond. Cosmic coincidence. What are the odds that two cosmic forces, one as vast and ancient as the Sun's magnetic field, the other a fleeting interstellar visitor, would collide in timing so precise that even seasoned forecasters hesitate to call it chance? On the very day 3I Atlas crossed the ecliptic, the invisible scaffolding of our star seemed to twist, like a great cosmic rope suddenly snapping into a new configuration. Scientists who have spent their careers charting solar cycles describe magnetic field shifts in terms of decades, not days. Yet here it was, a sudden reorientation, as though some external hand had brushed against the sun. The event was not announced with fanfare. It emerged in subtle indicators: disturbances in solar wind direction, sudden deviations in heliospheric current sheets, and unexpected readings in spacecraft instruments. Taken alone, such signals might pass as quirks of a star known for its volatile moods. Taken together in the precise window of an interstellar crossing, they strike at the heart of coincidence itself. The sun is not static. Its magnetic field constantly evolves in rhythm with its 11-year cycle, waxing and waning in polarity. But these shifts, charted over centuries of observation, have a certain predictability. The timing of this twist, coming just as 3I Atlas threaded its way through the ecliptic plane, was like hearing a sudden note played out of key during a familiar symphony. It jarred the models, leaving forecasters puzzled and, in some cases, publicly admitting they couldn't account for it. When the magnetic field twists, solar plasma follows. Charged particles spiral along altered lines, currents ripple through the corona, and the balance of solar wind pouring into the heliosphere shifts. To Earth, these are not abstract mechanics. They are the difference between calm skies and sudden geomagnetic unrest. That unrest arrived in ways too sharp to ignore. Instruments recorded a surge in solar wind density and velocity, and auroral zones on Earth flared with unusual intensity. Northern lights danced far below their expected latitudes and sweeping into regions where residents had never seen them before. At the same time, instruments measuring the Earth's magnetosphere reported compression, as though the invisible shield was being pressed inward by forces beyond the forecast. These were not ordinary ripples. They carried a signature of timing, locked to the crossing of 3 Atlas, as if the visitor's path had whispered through the solar system and left a fingerprint on the sun itself. Skeptics caution against drawing straight lines where none exist. Solar activity, they remind us, is capricious. Flares can erupt without warning, CMEs can surge with little prelude, and magnetic fields can shift in response to hidden subsurface dynamics. And yet timing remains the stubborn specter haunting this narrative. The sun's vast cycles are like seasons, rolling forward in slow arcs measured over decades. For a twist to appear just as an alien object brushed our system's equatorial plane, this is the kind of synchronicity that statisticians call improbable and storytellers call inevitable. Observers turn back to 3I Atlas, seeking some explanation in its nature. This wasn't just another comet from the Kuiper Belt or Oort cloud. Its hyperbolic orbit and interstellar origin were confirmed early on. It came not as a regular member of our celestial neighborhood, but as a wanderer from the dark between stars. Its passage through the ecliptic was no small event. It was a rare intersection of trajectories across different realms of space. That its crossing aligned with a solar magnetic anomaly created a riddle both scientific and symbolic. Can an object of dust and ice truly tug on the threads of a star's magnetism? Or is this merely the universe weaving its coincidences more tightly than we dare to accept? Adding to the unease was the character of the anomaly itself. It wasn't just a flicker or a small twist, it bore hallmarks of deeper reconfiguration. Forecasters described the heliospheric current sheet, a vast, spiraling surface of magnetic polarity extending through the solar system, as showing unexpected warps. Like a cosmic curtain pulled taut, it had bent at the very moment 3I Atlas crossed its plane. Data from spacecraft, SOHO Stereo, Parker Solar Probe, fed back images and magnetic readings that hinted at subtle but undeniable shifts. The models, built to anticipate Cycle 25's trajectory, began to show divergence. Predictions faltered. Some admitted the noise in their data was becoming the signal itself. For those who monitor space weather, the implications were unsettling. Magnetic twists on the sun ripple outward into everything. They change how CMEs are directed, how solar wind drapes around planetary magnetospheres, even how radiation belts swell or contract. A single twist, timed wrongly, can mean the difference between a harmless auroral display and a geomagnetic storm capable of disrupting satellites and grids. And so the question formed, whispered at first and then voiced more openly. Had 3 Atlas done something? Not through gravity, it was far too small. Not through mass, it lacked the heft to stir the sun. But through presence, timing, and coincidence, it had carved a place in the narrative of Solar Cycle 25. Patterns in nature often reveal themselves through timing. Earthquakes clustered after eclipses, auroras blooming after solar flares, meteors streaking during certain alignments. Most are explained away, others remain debated. Yet timing is the most human of measures, the one we cling to when causality slips away. This cosmic coincidence, an interstellar crossing and a solar twist, was timing writ large on the stage of the solar system. To dismiss it outright felt unsatisfying. To accept it without proof felt unscientific. And so the story lingered, suspended in the space between evidence and implication. Speculation filled the void. Could charged particles trailing 3 Atlas have interacted with solar wind streams? Could the comet's dust, rich with exotic compounds, have seeded instabilities along magnetic lines? Or was the visitor merely a bystander, a silent witness to the sun's own unpredictable theater? Each possibility led back to the same haunting realization. We don't yet understand how deeply the cosmos intertwines its events. Forecasters baffled, observers unsettled, and a public only dimly aware that something strange had just unfolded above their heads. As days passed, reports continued to surface. Sunspot numbers defied prediction, peaking earlier than anticipated. Auroral photography spiked across social media, dazzling those unaware they were witnessing a symptom of deeper unrest. In scientific circles, papers began to circulate quietly, some hesitant, others bold, asking whether Solar Cycle 25 was already breaking the mold. If the sun can twist unexpectedly, what else might it do as this cycle matures? And if interstellar visitors can align with such events, how often has history recorded synchronicities we failed to recognize? The coincidence cannot be proved nor disproved with the data we hold. It remains instead a question, sharp, unsettling, and open. Did 3 Atlas simply pass through our skies, leaving nothing but a faint dust trail? Or did it brush against the sun in ways unseen, reshaping a cycle, twisting a field, and leaving us to wonder whether coincidence is the universe's most powerful signal? Because what happened as the ecliptic crossing met the magnetic twist is more than an anomaly. It is a story of timing so precise, so cinematic, that it forces us to question whether the cosmos operates on rhythms we have only just begun to hear. And this was only the beginning. 3I Atlas's arrival. On July 1st, 2025, astronomers scanning the skies with the Asteroid Terrestrial Impact Last Alert System in Hawaii logged something they didn't expect. A faint point of light sliding across the star field at a trajectory too strange to belong here. Designated C 2025 A3 at first, then quickly reclassified as 3I Atlas once its hyperbolic path was confirmed, the object carried with it the weight of interstellar mystery. It wasn't just another comet from the frozen outer reaches of the Oort cloud. Its orbit didn't loop back toward the sun in the familiar elliptical arcs. Instead, it was unmistakably inbound from beyond, an interstellar visitor with no return ticket. The calculations unfolded quickly. Its orbital eccentricity exceeded 1.0, the clear mathematical marker of something not bound to our star. Early estimates placed its inclination at just a few degrees off the ecliptic plane, meaning its path cut directly across the flat planetary stage of our solar system. That alone made it a curiosity, because most interstellar objects are expected to arrive at steep, random angles. Yet this one seemed to slide almost neatly into the very plane where our planets orbit, like a stranger stepping uninvited into the center of a long-established family gathering. The coincidence gave pause, not only for orbital dynamicists, but for theorists who have spent years wondering just how common or uncommon such interstellar visitors truly are. Astronomers rushed to gather more observations. Images confirmed it was brightening faster than expected, its coma swelling with unusual vigor despite its distance from the sun. Early speculation suggested it was unusually volatile, perhaps carrying exotic ices that vaporized more easily than water, carbon dioxide, or carbon monoxide, the staples of solar system comets. Yet, even as it brightened, its spectrum revealed little of the usual fingerprints. No strong molecular emission bands, no clear atomic signatures. Instead, 3 Atlas presented itself as something halfway between a comet and a mystery. Dust-rich, gas-poor, glowing green under sunlight, yet giving up no obvious secrets about its chemistry. For those who remembered the saga of Oumuamua in 2017, the parallels were unavoidable. That earlier interstellar visitor had defied easy classification. Cigar-shaped or pancake-flat, depending on which model you preferred, accelerating slightly as though pushed by an unseen hand and leaving behind no visible tail. It had sparked debates that lingered for years, with some daring to suggest artificial origins. Then came 2I Borisov in 2019, which behaved more like a standard comet, releasing gas and dust in familiar ways. And now the third, the one named Atlas, arrived to split the difference, behaving partly like a comet, partly like a riddle. Its arrival sparked a storm of questions. How many such objects pass through our solar system unnoticed? Are we living in a cosmic crossroads where more interstellar travelers cross than our instruments can yet detect? And why now? Why during a solar cycle already showing signs of unpredictability? And why with an orbit that carried it across the ecliptic so neatly? The ecliptic is more than a geometric plane. It is the sheet on which planetary orbits, heliospheric currents, and solar magnetic fields are organized. To cross it is to touch the very fabric of solar dynamics, at least in symbolic terms. For 3I Atlas, that crossing happened just as the sun's magnetic field twisted, an alignment impossible to ignore for those watching closely. Even before it neared perihelion, 3I Atlas exhibited peculiar polarization properties. Light scattering off its dust cloud showed an unusually deep negative polarization branch, far beyond what is typically recorded in solar system comets. This suggested the dust grains themselves might be alien, not just in origin, but in physical makeup, forged under conditions absent in our star's nursery. Polarization studies often reveal the texture, porosity, and size of dust. What 3I Atlas revealed was something inconsistent, something that hinted at chemistry and formation environments far outside our familiar neighborhood. To call it otherworldly was not poetic license, it was the literal truth. As telescopes tracked its motion, one striking fact emerged. It was bright. Brighter than a body of its estimated size had any right to be. Calculations comparing its estimated nucleus size with its apparent magnitude suggested a paradox. Either it was far larger than thought, cloaked under a dense shroud of dust, or it was outgassing in ways that defied thermodynamic expectation. Some speculated that exotic volatiles, hydrogen cyanide, nickel compounds, or even unfamiliar ices could explain the discrepancy. Others proposed that fragmentation might already be underway, with smaller pieces breaking off and swelling the coma. Whatever the cause, its arrival was marked by a display that made clear this was no mere pebble drifting between stars. For planetary defense specialists, 3I Atlas's arrival raised another, quieter concern. Although its trajectory posed no direct threat to Earth, its near-ecliptic orbit meant it would sweep past the regions of space where planetary paths cluster. Even a harmless interstellar body passing near Mars or the asteroid belt carries implications. It can stir up smaller bodies, gravitationally nudge asteroids, or deposit exotic material into resonant orbits. Every interstellar arrival is, in effect, a small act of seeding, an injection of something foreign into the intricate orbital architecture of our system. That thought alone gave pause to those who think in centuries rather than weeks. The fascination deepened as amateur astronomers joined the hunt. Backyard telescopes confirmed the green hue of its coma, a shade often linked to diatomic carbon, but not in the intensity recorded here. Images posted online began to spread, drawing public attention to a story that until then had remained the province of scientific journals and press releases. To casual stargazers, it was a beautiful new comet. To researchers, it was a scientific anomaly. To forecasters already grappling with solar cycle 25's volatility, it was a harbinger of inconvenient timing. Its speed was staggering. Calculations revealed it was racing through the solar system at tens of kilometers per second, far faster than any body bound by the sun's pull. That velocity confirmed its interstellar origin. It would not stay, it would not loop back, it would not return. Its arrival was an event of opportunity, a brief window to study the material of other stars, other disks, other worlds, before it vanished forever into the dark. And yet, as it carved its hyperbolic arc, the coincidences stacked higher. The sun twisted. Space weather wavered. Auroras flared in strange places. Data lagged, models stumbled, and observers found themselves whispering the word pattern where before they had spoken only of chance. Arrival is never neutral. It carries with it expectation, disruption, reorientation. 3I Atlas's arrival did all three at once. It expanded the catalog of interstellar bodies from a novelty into a trend, suggesting our solar system may be intersecting more interstellar debris streams than we realized. It disrupted the models because its behavior did not align neatly with cometary templates. And it reoriented discussion around solar cycle 25 because its ecliptic crossing coincided so perfectly with a solar anomaly. In science, one coincidence can be ignored. Two are harder. Three begin to demand explanation. By late summer, as 3I Atlas's trajectory carried it closer to the sun, the buzz had shifted. No longer was it simply about an interstellar body. It was about what that body's presence revealed in the larger cosmic dance. Did it influence the sun directly, or was it a silent traveler whose timing exposed the fragility of our models? Was it coincidence, correlation, or something deeper? An unseen rhythm tying together wandering bodies and stellar cycles. In the end, its arrival marked more than just the passage of a visitor from another star. It marked a moment in which observers across disciplines, astronomers, heliophysicists, forecasters, found themselves grappling with the same unsettling truth, that the cosmos can stage alignments so precise, so cinematic, that they unsettle even the most rational minds. 3I Atlas's arrival was not just an event to be logged. It was a mystery that reminded us our solar system is not an island, but a crossroads where visitors arrive, stir the air, and vanish, leaving us to question what their timing really means. Anomalous brightness. From the moment astronomers fixed their telescopes on 3I Atlas, one fact became impossible to ignore. It was far too bright for what it was supposed to be. For an interstellar body discovered at a considerable distance from the sun, its luminosity defied expectation. Brightness, in cometary science, is a puzzle with many variables. Size of the nucleus, activity of volatile ices, density of dust, reflectivity of its surface. But when the numbers were compared, the equations didn't balance. The light streaming off 3I Atlas was more than its estimated size should allow, leaving researchers facing a paradox they could not immediately resolve. Brightness anomalies in comets are not unheard of. Some flare unpredictably, releasing jets of volatile material in sudden bursts. Others remain faint until perilously close to the sun. Yet, the intensity of 3I Atlas at such an early stage in its journey made seasoned observers uneasy. The standard models used to predict magnitude against distance broke down. Extrapolations suggested that at perihelion, the object could blaze far more brilliantly than expected, perhaps even becoming visible to the naked eye under dark skies. But the real intrigue lay not in what the public might see, but in what the brightness implied about the object itself. Was the nucleus much larger than initially estimated, hiding under a dense shroud of dust? Or was something in its composition causing light to scatter in ways unseen in local comets? The brightness seemed inflated, not entirely by reflective ice, but by the expansion of an abnormally thick coma. Dust poured from 3I Atlas in quantities that defied its modest nucleus size estimates, as though some alien chemistry was driving sublimation at a scale disproportionate to its mass. This led to one of the first speculative ideas that the interstellar environment in which it formed created ices more volatile than any our system knows, compounds that ignited under faint sunlight and produced an exaggerated glow. Some suggested hydrogen cyanide, nickel-rich compounds, or even cryogenic supervolatiles that release energy explosively when heated. The brightness, then, was not just a reflection, but a revelation, an outward sign of chemistry born under another star. If true, every photon collected from 3I Atlas carried the signature of a foreign system, encoded in dust and gas that had never before touched our sun's light. This was not just brightness, it was evidence, glowing green against the black canvas of space. And yet, anomalies often have more than one explanation. Some researchers pointed to fragmentation. If 3I Atlas was breaking apart even subtly, its dust output would skyrocket. Cometary nuclei are fragile, often riddled with cracks and voids. An interstellar body, shaped by eons of cosmic rays and thermal cycling, might be even more brittle. Each fracture could shed vast clouds of fine dust, inflating its coma and brightening its magnitude beyond reasonable limits. If so, then the brightness was a warning. This object might not survive its journey intact. What we were witnessing could be its slow unraveling, glowing brightest in the act of self-destruction. But there was a deeper problem with that theory. Normally, fragmentation leaves signs, asymmetries in the coma, jets streaming from the nucleus, sudden changes in trajectory as pieces shed momentum. 3I Atlas showed none of these in the early stages. Its coma was oddly uniform, its path unwavering. The brightness, instead of fluctuating wildly, had followed a surprisingly smooth curve, too smooth, some argued, for a body in pieces. That left researchers staring again at the data, wondering whether this was truly a comet in distress or something fundamentally different. The comparison with past interstellar visitors deepened the mystery. Oumuamua, the first known interstellar object, had been notoriously faint, barely visible even through powerful telescopes. Its brightness-to-size ratio was low, its surface dark and non-reflective. 2I Borisov, by contrast, had behaved more like a typical comet, with brightness corresponding to its activity. But 3I Atlas fell outside both templates, far brighter than its size, with activity patterns that made no sense when matched against our cometary playbook. It became, in essence, a third category, rewriting expectations and forcing astronomers to ask whether interstellar bodies follow rules of their own. The public narrative often missed this nuance. News outlets spoke of a bright green comet, a picturesque visitor for backyard telescopes. But behind the scenes, specialists were uneasy. Brightness is more than spectacle. It is a clue to mass, density, and chemistry. If the numbers don't match, it means the models are wrong. And when models break down at the intersection of interstellar matter and solar radiation, the implications ripple outward into everything we think we know about cometary science. Another possibility emerged, unsettling in its implications. What if the brightness wasn't entirely natural? Dust, after all, can scatter light in ways that mimic luminosity. An unusually fine distribution of particles could act like a cosmic lens, amplifying reflected sunlight. Was it possible 3I Atlas carried such a dust halo, either from fragmentation or from a primordial envelope formed in its parent system? If so, its coma might represent material untouched since the birth of alien stars, a pristine sample glowing under the sun's gaze. The brightness, then, would be less about present activity and more about ancient history preserved in drifting grains. Skeptics countered with caution. Overestimating anomalies has burned astronomers before. Comets have flared spectacularly, only to dim and fragment into obscurity by the time of public attention. The brightness of 3I Atlas could simply be a quirk, a temporary surge, a reminder that comets, interstellar or not, are volatile creatures. Yet, the timing with the sun's magnetic twist made dismissal harder. If the brightness anomaly coincided with solar anomalies, then what looked like coincidence began to feel like pattern. Were we watching a feedback loop, with the sun's activity amplifying cometary outgassing and the comet's dust interacting with solar wind in return? Instrumentation deepened the puzzle. Polarimetric measurements showed the scattering behavior of its dust was unlike anything in the solar system. The brightness wasn't just excessive, it was strange in color and polarization, as though the very properties of the particles were alien. This bolstered the hypothesis that we were seeing dust forged under foreign conditions. Different pressures, different elemental ratios, perhaps even within a star-forming region unlike our own. Each grain reflecting sunlight from 3i Atlas was, in a sense, a message from elsewhere, written in light too bright to ignore. The anomaly pushed forecasters to reconsider their tools. If brightness couldn't be predicted, then neither could the risks it posed. Outbursts, dust clouds, or fragmentation events could affect spacecraft, planetary atmospheres, or even Earth's own skies. When brightness defies the models, the future becomes uncertain. Some warned that dust trails left by 3i Atlas might intersect planetary paths years or decades later, creating meteor storms of alien origin. The sheer scale of its glow hinted at a massive material that would not vanish quickly. And still, the central question lingered. Why so bright? Why now? Why this object at this moment, as solar cycle 25 surged beyond expectations? The anomaly refused resolution, becoming instead a focal point for speculation. Some whispered of artificiality, echoing the debates around Oumuamua. Was the brightness a byproduct of reflective materials, engineered rather than natural? No evidence supported this, yet the lack of explanation left room for imagination. Others stayed grounded in science, pointing to exotic volatiles or fine dust, but all agreed the anomaly was real and it demanded attention. In the cosmic detective story unfolding, anomalous brightness became one of the earliest and clearest signs that 3i Atlas was not just another interstellar rock. It was a riddle written in photons, a glow that spoke louder than any trajectory or spectrum. For forecasters, it was a challenge. For astronomers, it was a gift. For those watching patterns between sun and comet, it was a warning. The brightness told a story, and the story was this: sometimes the universe reveals its strangeness not in shadows, but in light that burns brighter than reason allows. Polarization mystery light carries secrets. When sunlight bounces off dust, ice, or gas, it doesn't just brighten the sky, it twists, bends, and polarizes, revealing the hidden properties of the material it touches. Polarization studies are like fingerprints for cosmic dust. They tell us about particle size, structure, and even the environment in which those grains formed. For comets in our solar system, polarization patterns have been studied for decades, and though variations exist, they fall within a range. Then came 3i Atlas, and the rules were shattered. As astronomers turned polarimeters toward the interstellar visitor, they saw something startling: a deep, extreme negative polarization branch. This meant that at certain scattering angles, instead of reflecting light in expected patterns, the dust grains scattered it in an inverted, anomalous way. Negative polarization does occur in comets, usually at small phase angles, but the depth and persistence of the effect in 3i Atlas was unprecedented. It suggested the dust grains were not just foreign to our system in origin, but fundamentally different in texture and composition. Imagine holding a prism up to a beam of light and finding that the rainbow bends the wrong way. That's the scale of shock astronomers felt. Polarization isn't supposed to deviate this far, not unless the dust grains themselves are structured unlike anything in the solar system. Typically, cometary dust is porous, made of silicates, carbon compounds, and frozen ices with well-understood scattering properties. But 3i Atlas seemed to carry dust forged in an alien furnace, perhaps larger aggregates with smoother surfaces, or perhaps nanostructures formed in stellar nurseries with different elemental abundances. Even more baffling was the delayed inversion angle. In most comets, the polarization pattern flips from negative to positive as the scattering angle increases. With 3i Atlas, the flip point occurred far later, suggesting the grains held onto their anomalous scattering longer than expected. This delay raised eyebrows. Was the dust unusually compact, metallic, covered in thin organic films hardened by interstellar radiation? Every hypothesis pointed to environments not present in our solar system, reinforcing the idea that 3i Atlas carried within it a sample of conditions utterly alien. The anomaly could not be dismissed as noise. Independent observatories confirmed it, from professional arrays to smaller university telescopes equipped for polarimetry. The pattern held across different instruments, eliminating the possibility of error. And as the data accumulated, the implications deepened. If the dust of 3i Atlas was so fundamentally different, then each particle drifting through its coma was a relic of another star system's history, To study it was to peer into the chemistry of worlds that may have long since vanished. The mystery unsettled scientists because polarization is usually a quiet, dependable tool. It rarely produces surprises. In the case of 3I Atlas, however, polarization became the headline. The anomaly was too great to brush aside, and the timing too uncanny to ignore. Just as the sun twisted its magnetic field, just as brightness defied prediction, the polarization told a third independent story, that this object did not play by solar system rules. What could produce such an effect? One possibility is that the dust grains were coated in exotic ices like ammonia or methane clathrates that sublimated differently under sunlight. Another is that interstellar cosmic rays had altered their surface chemistry, carbonizing or crystallizing them in ways absent from our local environment. A third, more speculative idea suggested metallic inclusions, tiny flecks of nickel or iron that altered scattering properties dramatically. In all cases, the conclusion was the same. These grains were alien. They had been formed under physical and chemical conditions absent in the disk that birthed our sun. For some, this revelation was thrilling. It meant 3I Atlas was a messenger, carrying physical samples of another planetary nursery into our observational reach. For others, it was unsettling. If interstellar dust differs so radically, what else might arrive in our system carrying properties we do not yet understand? Could such particles interact with solar magnetic fields in unexpected ways, perhaps even influencing events like the twist that baffled forecasters? The speculation was bold but unavoidable. Polarization anomalies were not just curiosities. They might be keys to deeper connections. The public rarely hears about polarization. It doesn't translate easily into headlines. Yet behind closed doors, this was one of the most dramatic aspects of 3I Atlas's story. Papers circulated quietly, noting unexpected negative polarization depth and delayed inversion. The language was cautious, but between the lines lay excitement. This was something new, something unexplained, something that could not be filed neatly under existing models. Comparisons were inevitable. No known comet in the solar system exhibited polarization this extreme. Even 2I Borisov, also interstellar, showed values that sat comfortably within the solar system's normal range. 3I Atlas, therefore, stood alone. 3 interstellar objects had been cataloged, and of them, only Atlas displayed this extraordinary trait. The implication was unavoidable. Not all interstellar bodies are alike. Some may carry dust that challenges the very physics of light scattering as we understand it. The scientific implications ripple outward. If dust grains can vary so much between systems, then so can planet formation, atmosphere evolution, and even the habitability of worlds. Polarization anomalies are not just technical quirks. They're evidence that the chemistry of life, or the absence of it, may be deeply tied to the birthplace of dust. The alien fingerprints carried by 3 Atlas whisper of worlds we will never see, but whose dust now drifts into our skies. But there is another layer, one of timing. The polarization mystery unfolded during the same window as solar anomalies and geomagnetic unrest on Earth. Though no direct link can be proven, the convergence is unnerving. Dust interacting with solar wind, altering plasma scattering, or even seeding instabilities in the heliosphere. These are speculative ideas, but they gain weight when anomalies pile on top of one another. What are the odds that brightness, polarization, and magnetic twists would all peak in the same narrow window? For some, coincidence was too thin a word. To skeptics, polarization anomalies remain just that, oddities of dust, significant only to specialists. But to those looking for patterns, they stand as a third signal in a chain of mysteries. First brightness, then magnetic coincidence, then polarization. Each by itself might be explainable. Together, they sketch the outline of something larger, a hidden rhythm pulsing through solar system dynamics and interstellar arrivals. As the data continues to be parsed, one truth remains. Polarization stripped away the illusion that 3I Atlas was just another comet. It branded it as different in a measurable, undeniable way. Not theory, not speculation, but observation. The light did not behave as it should. That is the essence of science's most haunting moments, when the cosmos shows you something that does not fit. And so the mystery lingers. Dust grains drifting in alien light, carrying within them the secrets of unknown stars. A negative polarization branch deeper than any seen before, as though the comet itself resisted being understood. a delayed inversion, stretching the laws of scattering to their breaking point. Each observation a reminder that interstellar space is not uniform, but diverse, rich, and full of surprises. The polarization mystery of 3I Atlas is not merely a technical anomaly. It is a warning that our frameworks are incomplete, our models provincial, our understanding bound by local examples. Out there, in the void between stars, dust evolves differently, and when it drifts into our system, illuminated by our sun, it tells us, clearly in the language of light, that we are still only scratching the surface of the universe's complexity, and what it leaves behind is more than just data. It leaves the unsettling sense that light itself can carry messages from other worlds, and that those messages, once decoded, might force us to rethink everything we know about the origins of stars, planets, and perhaps even life itself. Spectral oddities. When astronomers want to decode the chemistry of a comet, they turn to its spectrum. Every atom and molecule emits or absorbs light at specific wavelengths, leaving behind a barcode of lines that reveal what it's made of. With 3I Atlas, researchers expected to find the familiar fingerprints of water vapor, carbon monoxide, carbon dioxide, cyanogen, or simple hydrocarbons, substances that have defined cometary chemistry for centuries. But as telescopes dispersed its light into spectra, the results were wrong. Not absent, not empty, but perplexingly muted, blurred, and incomplete. The most striking feature was the absence of strong emission lines. Most comets near similar distances from the sun display bright molecular bands as sunlight excites their gases. Yet 3 Atlas seemed to glow without them, as if its light came from dust scattering rather than volatile gas emissions. Its green hue, often attributed to diatomic carbon, didn't match the expected intensity or distribution. Instead, the spectrum showed weak traces, bare hints of gas, overwhelmed by a broad, dust-dominated continuum. This suggested that its coma was not only unusually thick, but chemically unusual, possibly reflecting an alien balance of volatiles. For some, the silence of the spectrum was more shocking than any anomaly of brightness or polarization. Light without lines is like a story without words. It means either the gas is absent or its composition is unlike anything in our catalogs. And if 3I Atlas lacked familiar volatiles, then what exactly was driving its activity? Dust alone cannot explain the scale of its coma. Something unseen, perhaps an exotic volatile, perhaps a slow, distributed release of unknown compounds, was feeding its glow. Comparisons with past interstellar visitors deepen the puzzle. 2I Borisov, discovered in 2019, behaved like a typical comet chemically. Cyanogen bands, carbon monoxide signatures, even water, all present and measurable. 1I Oumuamua, by contrast, had no detectable gases at all, behaving more like a rocky shard. But 3I Atlas sat awkwardly between the two extremes, too dusty to be barren like Oumuamua, but too chemically quiet to be a classic comet like Borisov. In doing so, it created a third template, a silent but dusty interstellar archetype that no one had predicted. Spectroscopists worked through possibilities. Could solar radiation be breaking molecules apart faster than they could fluoresce? Could interstellar radiation have already eroded the surface, leaving it depleted of common ices? Or was 3I Atlas carrying compounds with emission signatures outside the optical range being studied? Hidden, perhaps, in ultraviolet or infrared bands beyond the reach of most amateur and mid-range instruments. Each explanation brought with it implications that rippled outward. If interstellar comets carry different volatile inventories, then every star system seeds space with a different chemical fingerprint. And in 3 Atlas's case, that fingerprint was written in missing lines. The dust-to-gas ratio of the comet became a point of contention. Measurements suggested a coma overwhelmingly dominated by dust, with almost negligible gas production. This ratio was far outside the norm for solar system comets, most of which exhibit strong gaseous activity. It raised the question, was 3I Atlas once rich in volatiles only to lose them during eons of interstellar drift? Or was it born in a protoplanetary disk where dust dominated from the start, producing a fundamentally different kind of body? Either scenario points to formation processes unlike those that shaped our Kuiper belt or Oort cloud. Another curiosity lay in the broad absorption troughs seen in some spectra. Instead of sharp lines, observers recorded faint depressions across wide swaths of the optical spectrum. Some speculated these were caused by complex organics, tholins or carbon-rich polymers, coating its dust grains. Such materials are known to form in the outer reaches of planetary systems when radiation cooks simple ices into tar-like residues. If 3I Atlas carried these coatings, it could explain both the spectral oddities and the unusual polarization measured earlier. But more importantly, it meant the comet might be carrying prebiotic chemistry forged under alien stars. The muted spectrum also posed a practical challenge. Without clear gas lines, measuring its outgassing rate became nearly impossible. Normally, astronomers track specific bands to calculate how much material a comet is shedding per second. For 3I Atlas, estimates were shaky at best. Its brightness suggested heavy activity, but its spectrum whispered silence. Some argued that we were seeing non-traditional outgassing mechanisms, perhaps sublimation from deep layers venting through porous dust, or chemical reactions unique to exotic ices. Others suggested the dust itself could contain volatile-rich inclusions, releasing gas only when grains fragmented, producing diffuse and hard-to-detect signals. The lack of lines also prevented accurate measurement of its isotopic ratios. For solar system comets, these ratios, hydrogen to deuterium, carbon isotopes, nitrogen isotopes, are critical clues to their birthplace. With 3I Atlas, those ratios remained locked away. This was perhaps the greatest frustration for planetary scientists. An interstellar messenger had come within range, carrying chemistry from another world, but it refused to yield its secrets in the spectral language we know how to read. Still, anomalies often drive science forward. The absence of expected features forced researchers to expand their models. Could there be new categories of volatiles we've never cataloged? Compounds stable in interstellar space, but unstable under solar heating, producing transient signals invisible to standard instruments? Could the green glow itself be misleading, perhaps enhanced by unusual dust scattering rather than molecular emission? Each hypothesis only deepened the sense of mystery. Some speculations went further, skirting the edge of mainstream discourse. Could the spectral silence indicate an artificial surface? Highly reflective dust engineered or altered to scatter light without gas release. This echoed the debates around Oumuamua, where its acceleration and lack of gas led Avi Loeb and others to suggest a technological origin. While most dismissed the idea for 3 Atlas, the spectral anomalies reopened the door for speculation. Why would a comet-like body shine so brightly without the chemical voice of ordinary volatiles? Yet the most unsettling aspect of all was timing. The period when 3I Atlas displayed its oddest spectra coincided with the solar magnetic twist that caught forecasters off guard. In the same window of weeks, geomagnetic storms rattled Earth's magnetosphere, auroras descended to unusual latitudes, and seismic murmurs cropped up in regions not known for large quakes. Individually, none of these events could be tied directly to the comet, but collectively, they painted a picture of a cosmos out of balance, where a visitor from the stars, silent in spectrum but loud in presence, seemed woven into a broader pattern of disruption. This is the paradox of 3I Atlas's spectral oddities. Its silence speaks louder than noise. It is not what the comet showed us that matters, but what it refused to reveal. In its absence of lines, we are confronted with questions about the diversity of planetary systems, the chemistry of alien nurseries, and the limits of our instruments. We are reminded that the universe does not owe us answers, only opportunities, and sometimes those opportunities arrive cloaked in dust, glowing green, and whispering nothing. And so, the story of 3I Atlas's spectrum is not one of discovery, but of provocation. It provokes us to rethink assumptions, to broaden models, to prepare for the next interstellar visitor. Because if one body can be this strange, how many others might pass unnoticed, carrying secrets our telescopes aren't yet tuned to hear? The silence of its spectrum may in time prove louder than the brightest comet in history. And just as its light fades into the black, the questions it raised blaze brighter still. Trajectory versus ecliptic crossing. The moment orbital calculations confirmed 3I Atlas would intersect the ecliptic plane, a ripple of unease moved through the astronomical community. Interstellar objects are expected to arrive at odd, steep angles, slicing through our system like arrows shot blind into the night. But 3I Atlas did something different. Instead of taking a reckless path across the tilted architecture of our planets, It threaded the needle, crossing almost flush with the very plane that defines our solar system's geometry. It wasn't just unusual, it was statistically startling. The ecliptic is more than a mathematical convenience. It is the thin disk where the planets formed, where the sun's gravitational grip flattened dust and gas into a rotating sheet. Every major planetary orbit lies within a few degrees of it. Comets and asteroids born in our system tend to align loosely with this plane. But outsiders, interstellar visitors, should not. Their random origins should scatter their paths in every direction. For one to arrive aligned so neatly is like finding a tossed coin balanced perfectly on its edge. Not impossible, but improbable enough to make you look twice. When 3I Atlas was first spotted on July 1st, 2025, its hyperbolic trajectory marked it clearly as an interstellar object. Its eccentricity, greater than 1, proved it would not be captured by the sun. But what raised eyebrows was its low inclination, only about 5 degrees off the ecliptic. That number meant it wasn't plunging steeply through the solar system like Oumuamua, which cut across at a 123-degree tilt, nor was it tilted dramatically like Borisov at 44 degrees. Instead, 3I Atlas skimmed the very plane of our system, sliding into alignment with planetary orbits as though it had been guided. This peculiar trajectory carried consequences. By crossing near the ecliptic, 3I Atlas passed close to the gravitational domains of planets, resonant regions, and solar wind structures concentrated along this plane. The intersection raised the likelihood of interactions, not impacts, but subtle exchanges of dust, magnetic coupling, or gravitational nudges. For planetary scientists, the alignment was a rare chance to observe an interstellar object under conditions where solar system dynamics are strongest. For those inclined to speculate, it was almost too convenient, an outsider arriving at the one place where it could matter most. Timing compounded the unease. Just as 3I Atlas crossed the ecliptic, the sun's magnetic field underwent a sudden twist, baffling space weather forecasters. The heliospheric current sheet, an enormous spiraling surface of polarity, was warped in unexpected ways. To many, the coincidence was nothing more than that, coincidence. But the alignment made the imagination leap. Could dust or plasma from 3I Atlas have seeded instabilities along the current sheet? Could its charged tail have brushed against solar wind streams, amplifying turbulence at the very moment of crossing? The science is uncertain, but the geometry is undeniable. The crossing and the twist happen together. The geometry itself is a story. Imagine the solar system as a vast cosmic turntable, with the planets circling in a thin groove. Now picture an interstellar object arriving not from above or below, but sliding nearly along that groove. The odds of such an alignment are small, but once it happens, the potential for resonance multiplies. Any dust trail left behind intersects with planetary orbits. Any plasma interaction happens where solar wind flows are densest. Any observational campaign gains the advantage of perspective, since instruments positioned along the ecliptic can more easily track and study the body. For centuries, astronomers have treated the ecliptic as a stage where cosmic events play out most visibly. Eclipses, conjunctions, and alignments all unfold there. For 3I Atlas to choose this stage, whether by accident or cosmic design, gave its passage a theatrical quality. The fact that its arrival coincided with a solar anomaly turned the stage into a drama. Scientists who normally scoff at meaning in coincidences were forced to acknowledge the striking optics. A visitor from the stars crossing the system's central plane, just as the sun itself reshaped its invisible architecture. But beyond optics, there are mechanics. By aligning so closely with the ecliptic, 3I Atlas opened the door for long-term dynamical effects. Dust released from its coma could spread along orbital paths, intersecting with planetary regions years or decades later. Meteor showers on Earth, strange bolide events on Mars, or subtle darkening of solar panels on spacecraft all could trace back to material seeded by this crossing. Interstellar dust rarely has the chance to integrate into the disk of our system. 3I Atlas may change that. The path also offered a unique laboratory for spacecraft observations. Missions like Parker Solar Probe and Solar Orbiter, already orbiting near the ecliptic, found themselves well positioned to detect outflow from the comet. Instruments sensitive to dust, plasma, and charged particles could sample alien material without leaving their tracks. The ecliptic crossing, therefore, was not just symbolic but practical, an interstellar experiment delivered to our doorstep. Yet for all the science, the oddness of the trajectory lingered. Why this plane? Why now? Why in the middle of solar cycle 25's volatility? Was the alignment purely chance, the kind of coincidence that only feels strange because humans are wired to notice patterns? Or was there something deeper, a selection bias in what kinds of interstellar objects we detect, perhaps favoring those that align with the ecliptic? Some theorists proposed exactly that. Telescopes scanning along the planetary plane are more likely to catch low-inclination objects. Perhaps many steeply angled visitors slip by unnoticed, leaving only the aligned ones in our records. If so, then 3 Atlas might not be unusual at all. It might only reflect the way we look at the sky. But even if detection bias explains part of the story, it cannot erase the timing. The sun's magnetic twist happened in lockstep with the crossing. Earth's magnetosphere wavered, auroras surged. For those inclined to connect dots, the geometry was fuel for speculation. The ecliptic is not just any plane, it is the stage where solar, planetary, and interstellar forces collide most visibly. And on that stage, 3I Atlas's trajectory became a character in a larger play, one whose script remains unfinished. Some researchers reached further into speculative territory, wondering whether low-inclination interstellar visitors might follow galactic structures. Our solar system itself orbits the Milky Way within a thin disk. If interstellar comets are ejected preferentially along the equatorial planes of their parent systems, then perhaps most wanderers drift through galactic space in flattened distributions, like dust motes in cosmic light. In that case, 3I Atlas's alignment with our ecliptic may not be accident, but resonance, a reflection of galactic geometry mirrored at solar scale. The idea is bold, but it reflects a growing awareness that our solar system is not isolated. It is embedded in a larger galactic environment where interstellar material, magnetic fields, and stellar winds constantly interact. The trajectory of 3I Atlas aligning so cleanly with our ecliptic may hint at unseen currents in that larger sea. Perhaps its path was shaped not by randomness, but by long-term galactic flows, delivering it precisely where its presence would resonate most. For now, what we can say with certainty is that 3I Atlas's path is extraordinary. Its crossing of the ecliptic at the very moment of solar upheaval is recorded fact. Its low inclination is measured reality. What those facts mean, however, is still open to interpretation. For some, it is a quirk of statistics. For others, it is a hint that patterns link interstellar visitors to solar activity. For all, it is a reminder that the geometry of space is never meaningless, but filled with alignments that can surprise, unsettle, and inspire. And so the trajectory of 3 Atlas is not just a line on a graph. It is a story of improbable alignment, a crossing that turned geometry into drama. It raises questions about how visitors move through our system, about how we detect them, and about whether coincidences are truly blind. Above all, it forces us to reconsider the ecliptic not just as the plane of planets, but as a stage where cosmic visitors arrive at moments too uncanny to dismiss. In the mystery of 3I Atlas, the line it traced across the ecliptic may prove to be one of the most telling signs of all. Solar magnetic field shift. The sun is not a silent star. Beneath its blinding surface, electric currents churn, magnetic fields twist and snap, and waves of plasma boil outward into space. For decades, scientists have charted its cycles, learning to expect the rise and fall of sunspots, the periodic flips of polarity, and the rhythmic breathing of solar wind. Yet every so often, the sun behaves in ways that defy prediction. That is what happened when 3I Atlas cut across the ecliptic, and at the very same moment, the sun's vast magnetic field shifted in a way that caught forecasters unprepared. At first, the signs seemed subtle. Instruments aboard spacecraft like the Parker Solar Probe, SOHO, and STEREO began registering changes in the solar wind's polarity. The heliospheric current sheet, the immense spiraling boundary that separates regions of opposite magnetic charge, was warped more than models anticipated. Instead of following the smooth undulations expected in solar cycle 25, the current sheet twisted sharply, as though jolted by an unseen hand. For those who live and breathe space weather predictions, it was an immediate red flag. The sun's magnetic field is a colossal structure, reaching far beyond the orbits of the planets, shaping the heliosphere itself. When it shifts, the effects ripple outward like a shockwave through water. Charged particles ride its lines of force, cosmic rays are deflected or funneled differently, and Earth's magnetic shield can find itself under sudden pressure. But what unsettled forecasters most was not the fact of the twist. It was the timing. The warp unfolded almost in lockstep with the moment 3 Atlas crossed the Ecliptic, the plane where magnetic fields and planetary orbits are most tightly wound together. Normally, magnetic field reconfigurations follow predictable rhythms tied to the sun's 11-year cycle. We expect peaks in activity, reversals at solar maximum, and calmer periods in decline. But this twist didn't fit the expected curve. Solar cycle 25 had already been stronger than forecasts suggested, with sunspot numbers outpacing predictions. Still, nothing in the models hinted at such a sudden global magnetic rearrangement. That it arrived in tandem with an interstellar visitor only deepened the mystery. Space weather forecasters pride themselves on caution. Their business is prediction. When geomagnetic storms will strike, how satellites will be affected, whether power grids might need to brace for surges. To admit bafflement is rare, yet baffled is precisely what many felt. Magnetometer data didn't add up. Solar wind models diverged wildly from observed readings. The twist was real, undeniable, and unexplained. Some quietly suggested that the sun had entered a phase of instability within cycle 25, one that models failed to anticipate. Others wondered whether something external, some trigger, had nudged the system into chaos. Speculation turned to 3i Atlas, not because it could realistically tug the sun's fields with gravity, it was far too small for that, but because its crossing of the ecliptic coincided with the field's warp. Could the interstellar dust it shed have acted as a seed for plasma instabilities? Could its charged particles, ionized by sunlight, have interacted with the solar wind just enough to create turbulence in the magnetic sheet? These were fringe ideas, but when anomalies align, the mind looks for links. The magnetic field shift was not just a curiosity, it had tangible consequences. Earth's magnetosphere compressed more than usual during this period, leading to auroras seen as far south as latitudes unaccustomed to them. Satellites recorded fluctuations in radiation belts. Airline pilots reported stronger than expected exposure alerts on high-altitude polar routes. Even amateur radio operators noticed strange propagation effects, with signals bouncing unpredictably as the ionosphere flexed under shifting magnetic influence. These disturbances formed a tapestry of evidence. Something in the sun's magnetic environment had changed, and changed dramatically. The scientific debate quickly split into 2 camps. The conservative side argued that solar activity often surprises us. This was simply another case of internal solar dynamics outpacing our predictive power. After all, magnetic reconnection events, stealth CMEs, and chaotic field line shifts are well-documented phenomena. The timing, they insisted, was coincidence. The more adventurous voices, however, pointed to the statistical unlikelihood. What are the odds that the most anomalous magnetic twist of the cycle would occur precisely as an interstellar visitor threaded through the solar system's heart? Patterns, they argued, demand attention, even if the cause remains invisible. Looking deeper, some researchers noted that the shift bore unusual characteristics. Instead of a gradual reorientation, the twist happened abruptly, almost violently, over a matter of days. Such rapid changes are rare in global-scale solar structures. It was as if the entire magnetic skeleton of the sun flexed at once, pulling the spiraling current sheet into a distorted shape. This distortion sent solar wind streams veering in new directions, hitting Earth and other planets with unexpected intensity. For Mars, which lacks a global magnetic shield, this meant direct atmospheric stripping, data that rovers and orbiters quietly logged even as the anomaly played out. The implications ripple further still. If the sun's magnetic field can shift so unpredictably, it challenges our ability to model solar cycles at all. Cycle 25 was already confounding expectations. Now it seemed capable of rewriting the rulebook entirely. What if interstellar objects like 3i Atlas aren't mere curiosities, but occasional wild cards in the solar cycle narrative? Could their passages trigger resonances, amplify instabilities, or expose weak points in the sun's magnetic armor? It's speculation, yes, but speculation born from timing too sharp to ignore. History provides eerie parallels. Ancient records describe auroras, sun darkenings, and unusual solar activity coinciding with comets bright enough to terrify entire civilizations. While correlation is not causation, the alignment of sky portents and solar unrest stretches back millennia. Three-Eye Atlas's crossing may be the modern echo of those stories, a reminder that even now, with instruments and satellites, we are still deciphering a cosmic language written in coincidence. The solar magnetic shift also reignited discussions about Earth's vulnerability. Our reliance on satellites, power grids, and communication networks makes us more fragile than ever to geomagnetic storms. If Cycle 25 produces more twists like this, unpredictable, sudden, and violent, the consequences could reach far beyond auroras. Some forecasters warned that this anomaly might be the prelude to larger disruptions, a hint that the sun is entering a turbulent phase we barely understand. And in the backdrop, the green interstellar visitor hangs, a silent witness, or perhaps a catalyst to it all. For now, no definitive link exists between Three-Eye Atlas and the solar twist, but science progresses by anomalies. Each unexplained shift forces us to refine models, reconsider assumptions, and prepare for the unexpected. The magnetic field anomaly of mid-2025 will be dissected for years, its data pored over by heliophysicists searching for overlooked clues. Was it merely an internal burp of the sun, or did an external visitor nudge its timing? The answers may remain elusive, but the questions it sparks ensure that this twist will not be forgotten. And so the story of the solar magnetic field shift is one of mystery layered upon mystery, a star that defies prediction, a visitor that arrives with impossible timing, and a planet caught in the middle, watching auroras flare and instruments tremble. Whether coincidence or connection, the alignment has left an indelible mark on the narrative of Cycle 25. The sun has spoken in a language of twisted fields and bent light, and Three Atlas passed across the stage at the same moment, like an actor entering exactly on cue. In the end, perhaps that is what unsettles us most. Not that the sun's magnetic field shifted, that much we know it can do, but that it chose this moment, aligned with an alien wanderer, to remind us that the universe does not always play by our rules. Sometimes it plays by its own, and we are left to wonder whether what we call chance is merely the surface of a deeper pattern waiting to be revealed. Solar storm surges. When the sun's magnetic field twisted in mid-2025, it didn't just shift invisible lines of force, it set loose a series of disturbances that cascaded outward like thunder after lightning. Space weather forecasters quickly realized they weren't looking at a simple hiccup in the solar wind. They were witnessing surges, sudden bursts of plasma, heightened radiation levels, and directional currents that defied prediction. The timing could not have been more unsettling, because these surges erupted almost in step with Three-Eye Atlas slicing across the ecliptic plane. For days before the anomaly, the sun had shown modest signs of activity. Sunspot regions bubbled across the photosphere, solar wind speeds hovered near expectations, and Cycle 25, though running hotter than early forecasts, seemed to be playing by its own aggressive rhythm. But within hours of the magnetic twist, things changed. Instruments onboard the Parker Solar Probe recorded a spike in solar wind density that surged far above modeled values. ACE and DS cover, monitoring solar wind at the L1 point, confirmed the same. Velocities increased by hundreds of kilometers per second, dragging with them elevated proton flux and turbulent magnetic fields. On Earth, the consequences appeared almost immediately. Auroras exploded across skies well beyond their usual boundaries, bleeding into latitudes where residents rarely see them. Reports from Southern Europe, the American Midwest, and East Asia described shimmering curtains of green and crimson dancing overhead, powered not by forecast CMEs, but by unexpected plasma surges. Airline pilots reported radiation exposure alerts. Satellites experienced anomalies, some briefly entering safe modes as particle fluxes surged through their shielding. It was as if the sun had emptied its lungs in a sudden, violent exhalation. But this was no ordinary storm. The surges came in waves, not as single, discrete events. Typically, a CME or solar flare arrives, strikes, and subsides. Here, the disturbances pulsed. Plasma densities rose, fell, then rose again, as though the sun were shuddering in sync with some external rhythm. Forecasters struggled to model the pattern. Their equations expected decays where surges reappeared, predicted calm where turbulence built instead. It was a storm without a template. Some theorists suggested that the twisting magnetic field had untangled stored energy, unleashing not one CME but multiple stealth eruptions, events without obvious surface flares yet potent in the corona. Others argued that interplanetary magnetic fields had been rewired, funneling solar wind toward Earth in ways not accounted for in simulations. The effect was clear: Earth's magnetosphere compressed and shook under the barrage. The KP index, a measure of geomagnetic activity, spiked higher than predicted, peaking at storm levels that caught operators of power grids and satellites off guard. And in the background of this sudden upheaval was the interstellar visitor, 3I Atlas, its trajectory aligned with the same ecliptic stage where the sun had chosen to erupt. Coincidence, most insisted, but timing has a way of infecting even the most skeptical minds. Could the comet's massive dust halo, ionized by solar radiation, have interacted with plasma streams? Could its crossing have seeded turbulence in the very currents now surging outward? No proof existed, but the suspicion lingered, like a shadow cast across the data. For Mars, the surges were even more dramatic. Without a global magnetic shield, the red planet bears the full brunt of solar storms. Orbiters detected sharp increases in atmospheric escape as charged particles stripped away oxygen and hydrogen at accelerated rates. Dust storms on the surface coincided with these surges, raising questions about whether solar inputs could influence weather patterns there. If 3I Atlas's crossing amplified solar instability, then its fingerprints might already be etched into Martian skies. The surges also carried unusual directional signatures. Normally, solar plasma streams follow predictable paths aligned with solar rotation and the Parker spiral. But during this anomaly, the streams bent. Measurements suggested that magnetic field lines were rechanneled, funneling energy at oblique angles. For Earth, this meant solar plasma approached from unexpected vectors, disrupting communications satellites aligned to resist typical orientations of solar wind. The anomaly wasn't just about strength, it was about geometry, if the invisible scaffolding of space weather warping in ways our models couldn't track. The unpredictability rattled space weather forecasters. Their role is to safeguard modern civilization, to give satellite operators time to power down, to let grid controllers brace for geomagnetic currents, to warn astronauts on the ISS when radiation storms make the void too dangerous. Yet, in this moment, their tools failed. Predictions lagged reality. By the time warnings were issued, the surges were already slamming into Earth's shield. For an age so dependent on satellites for navigation, communication, and surveillance, this failure was chilling. Digging deeper, some researchers noted that these surges carried energetic particle profiles unlike typical CME events. Proton counts were elevated, but their spectral distribution skewed strangely. Electrons showed bursts not aligned with expected magnetic structures. Some speculated that multiple stealth eruptions had overlapped, producing a blended profile. Others whispered that interaction with external dust or plasma, perhaps the extended coma of 3I Atlas, could have altered particle dynamics. Such speculation sits on shaky ground, but the timing of surges with the ecliptic crossing left too sharp a correlation for many to ignore. Looking outward, the heliosphere itself may have felt the pulse. Voyager and IBEX data hinted at changes in the boundary regions, though confirmation awaits. If surges propagate that far, then 3I Atlas's arrival may have coincided with an event reverberating across the sun's domain. Imagine a ripple extending billions of kilometers, born of a magnetic twist, amplified by plasma surges, marked forever by the passage of an interstellar visitor. The surges also reignited discussions about Solar Cycle 25's unpredictability. Forecasts had placed its peak around 2025 to 2026, but activity was already overshooting expectations. The mid-2025 surges suggested we might be entering a cycle more violent than models allowed. If one unpredicted twist can unleash this level of disturbance, what else lies ahead as the cycle intensifies? Could surges of this magnitude become common, or was this an isolated anomaly amplified by unlucky timing? The answers are not yet clear. For historians of science, parallels emerged. The Carrington event of 1859, the strongest solar storm on record, came without warning, its auroras dazzling the world and telegraphs sparking into flames. Smaller but disruptive events struck in 1921, 1989, and 2003. Each left behind the same lesson. When the sun surges unexpectedly, human infrastructure trembles. What made 2025 different was the cosmic coincidence, the presence of three Atlas, drifting silently through the very plane where storms now raged. The narrative becomes more than science at that point. It becomes story. Humanity watches auroras ignite skies never meant to glow, instruments falter, models fail, and a green interstellar wanderer hovers in the background, a silent guest at the feast of solar chaos. For the rational, it is chance. For the pattern seeker, it is synchronicity. And for the rest of us, it is a reminder that the sun's moods can shift in an instant, aligning with visitors from the stars in ways that make coincidence feel like conspiracy. The surges subsided, as all storms do. The magnetosphere recovered, satellites resumed normal operations, auroras faded back to polar latitudes. But the scars remained. Datasets riddled with anomalies, forecasters humbled, and speculation still smoldering in the academic underground. Was it merely the sun flexing its chaotic nature? Or was the timing with 3i Atlas the beginning of a story not yet finished? In the aftermath, one lesson stands out. We are still students of the sun, not masters of its rhythms. Each surge, each twist, each anomaly writes itself into a ledger we only half understand. And as 3i Atlas drifts farther from the inner system, the memory of those surges lingers like an echo. A reminder that sometimes the universe orchestrates alignments too sharp to dismiss, leaving us to wonder whether we are observing chance or the faint outline of a larger cosmic pattern. Forecasters express confusion. The language of space weather is supposed to be precise. Forecast models take in solar magnetograms, flare probabilities, solar wind speeds, and coronal hole maps, then produce neat outputs. Minor storm expected in 48 hours, or low risk of geomagnetic disruption. These predictions guide everything from power grid managers to satellite operators to airline routes. The one thing they are not supposed to do is fail catastrophically. And yet, in the days when 3i Atlas slipped across the ecliptic and the sun's magnetic field twisted, that is exactly what happened. Forecasters rely on the assumption that the sun's behavior, while turbulent, follows patterns tied to its 11-year cycle. Cycle 25 had already proved feistier than expected, but most still trusted the models built on decades of data. When the solar winds surged and the magnetic field warped in ways the forecasts hadn't predicted, it created something rare in the professional community: public bafflement. At first, the confusion came in whispers. Solar physicists exchanged notes that didn't align, velocity spikes no one expected, auroral activity out of phase with known coronal mass ejections, magnetospheric disturbances that rose and fell in unpredictable pulses. Instruments across agencies disagreed, not because they were faulty, but because the sun itself was breaking the rules. The forecasts issued in late June and early July 2025 proved embarrassingly wrong, warning of mild geomagnetic storms just as Earth was hit with waves strong enough to light auroras over Madrid and Chicago. The admission came reluctantly. NOAA's Space Weather Prediction Center and ESA's solar orbiter teams acknowledged the models had missed something fundamental. Analysts used words rarely seen in technical bulletins: unexpected, unprecedented, unmodeled. To a field built on cautious understatement, these words carried the weight of an earthquake. Behind the guarded language was something more personal: bewilderment. What had thrown them off balance? The twist in the sun's magnetic field was part of it. The heliospheric current sheet, usually predictable in its slow, spiraling dance, had warped violently. That warp redirected solar wind streams, making existing forecasts obsolete overnight. Yet the timing of this warp, so close to 3i Atlas's ecliptic crossing, gnawed at the edges of scientific restraint. Was the alignment pure chance? Or had the interstellar visitor played a role, however subtle, in magnifying the sun's volatility? Publicly, most forecasters refused to speculate. Privately, the conversation was different. Some noted that the brightness and dust activity of 3i Atlas might have created a vast, charged halo intersecting solar wind flows. Others wondered if the very presence of a hyperbolic body on such a low inclination path could have gravitational or plasma coupling effects still poorly understood. Even if the object itself did nothing, the timing felt orchestrated, a puzzle piece falling into place in a larger pattern. For forecasters accustomed to translating solar dynamics into reliable guidance, the breakdown was unsettling. Airlines had rerouted polar flights based on outdated risk assessments. Satellite operators had underprepared for radiation spikes. Amateur observers, ironically, had done better than professionals in sounding alarms, posting online images of auroras that should not have been there. The predictive system faltered, and with it, confidence in the ability to foresee the sun's moods. To understand the scale of their confusion, one must remember how far the science has come. In the 19th century, storms like the Carrington event of 1859 arrived without warning, catching telegraph operators off guard as sparks leapt from their equipment. By the early 21st century, forecasters prided themselves on multi-day warning systems, able to predict most large storms with hours to days of lead time. But July 2025 exposed the limits. Here was a case where predictions not only missed the timing, but the magnitude, that leaving the impression that the sun had shifted into a mode the models simply could not capture. The data didn't just fail, it contradicted itself. Some instruments showed plasma densities surging, others recorded calm. Magnetometers swung wildly from positive to negative. The fluctuations were so erratic that attempts to feed them into models produced nonsensical outputs. One team joked grimly that their forecast plots looked like a seismograph during an earthquake, not a solar forecast. Confusion hardened into embarrassment, and embarrassment shaded into a more dangerous recognition. If the models could fail this badly, then our technological civilization was more vulnerable than we like to admit. News outlets picked up on the story. Headlines read, "Scientists baffled by sun's behavior, auroras defy forecasts. Unmodeled solar twist stuns experts." For a public accustomed to hearing scientists speak with authority, the sudden humility was shocking. It fueled conspiracy theories that data was being hidden, that the interstellar comet had triggered something catastrophic, that governments were downplaying risks. In reality, the truth was simpler, but no less unsettling. The experts didn't know. Some voices in the forecasting community tried to restore calm. They reminded the public that the sun has always been unpredictable at small scales, that models are approximations, not guarantees. They emphasized that the link to 3I Atlas was coincidence, nothing more. Yet the timing hung in the air like static, refusing to dissipate. Each aurora photograph shared online, each amateur report of geomagnetic disturbances, reinforced the sense that something unusual had unfolded beyond the scope of known science. Behind the confusion lay deeper concerns about the future of forecasting itself. If Cycle 25 could produce twists and surges invisible to current models, how many more might follow as the cycle crested toward maximum? And what of Cycle 26 beyond that? Forecasting is not just academic curiosity, it is infrastructure defense. Power grids, communications networks, navigation systems, even basic internet stability depend on accurate predictions. The confusion in 2025 was not only scientific, it was existential for the systems we rely upon daily. Internally, forecasting agencies began re-examining their assumptions. Were they too focused on surface phenomena, sunspots, flares, while neglecting deeper subsurface currents that drive magnetic shifts? Had their reliance on historical cycles blinded them to novel behavior? And perhaps most controversially, should they begin factoring in the presence of interstellar bodies when assessing risk, not because those bodies directly alter the sun, but because coincidences may mask correlations we don't yet understand? For those willing to speculate, the confusion was fertile ground. Independent researchers pointed to patterns stretching back centuries, comets coinciding with solar storms, auroras recorded alongside celestial apparitions. Could 3I Atlas be part of a recurring phenomenon? Interstellar debris streams intersecting with the solar system at times that amplify solar instability. The mainstream dismissed these ideas as pattern-seeking. Yet in private, even skeptics admitted that the timing of July 2025 would haunt their models for years to come. The emotional toll on forecasters should not be overlooked. These were professionals whose work is built on being the guardians of preparedness. To stand before cameras and admit, "We don't know why this happened," was humbling, even humiliating. Yet it also marked a rare moment of scientific honesty. Confusion is not weakness. It is the first step toward discovery. and in the bafflement of July 2025, the seeds of new understanding were sown. In the end, what remains most memorable is not the storms themselves, but the admission of limits. For once, the experts stood shoulder to shoulder with the public, gazing upward at a sun that defied their expectations, and confessing that the universe had outplayed them. It was a moment both unsettling and strangely unifying, a reminder that beneath all our models and forecasts, we are still vulnerable to forces larger than ourselves. And as 3i Atlas receded into the black, leaving behind its glow and its mysteries, the memory of forecasters' confusion lingered. Perhaps it will be remembered as a turning point, when humility forced science to expand its models, to admit the gaps, to seek new truths. Or perhaps it will fade into history as another cosmic coincidence. Either way, the bafflement remains etched into the story of Solar Cycle 25, a chapter written in failed predictions, unexpected storms, and the silent passage of a green wanderer from the stars. South Atlantic anomaly and proton drop. Far from the glare of auroras and the storm-swept skies of the north, another anomaly unfolded quietly, hidden in the deep magnetic architecture of Earth itself. While forecasters wrestled with unexpected solar surges, instruments in orbit began recording something stranger still: a sharp decline in energetic protons within the region known as the South Atlantic anomaly. The South Atlantic anomaly, or SAA, has long been the weak spot in Earth's magnetosphere. Centered off the coast of Brazil and stretching across the South Atlantic Ocean, it is the place where our planet's protective magnetic shield dips lowest, allowing radiation to creep closer to the surface. Satellites passing through the anomaly are often bombarded by charged particles, forcing engineers to harden electronics and shut down sensitive instruments as they pass overhead. For decades, the SAA has been treated as a nuisance, a reminder that Earth's field is not symmetrical but lopsided, twisted by the molten dynamics of our planet's core. But in the weeks surrounding 3i Atlas's ecliptic crossing and the sun's magnetic twist, something odd occurred. The bombardment of energetic protons inside the SAA dropped, not rose. Instead of the usual spikes, instruments recorded unusually calm conditions, as though the anomaly itself had softened. Proton flux readings from multiple spacecraft aligned. Levels were falling in ways that couldn't be easily explained by local magnetospheric models. To some, this seemed like a stroke of luck, a rare reprieve for satellites vulnerable to radiation. But to scientists paying attention, it looked like a clue, a sign that deeper currents in the Earth-Sun system were being rearranged. Why would proton counts drop in the very region most prone to bombardment? Normally, the SAA acts as a funnel, letting high-energy protons and electrons bleed inward from Earth's radiation belts. When solar storms rage, the anomaly often lights up with increased particle activity. But in this case, the opposite happened. Some researchers suggested that the global reconfiguration of the sun's magnetic field had altered the shape of Earth's magnetosphere in ways not yet understood. If solar wind lines bent differently, perhaps the pathways that usually fed the SAA were temporarily blocked. Others posited that the proton decline could be evidence of a transition, a signal that the broader solar cycle was entering a phase shift. It was not the first time Earth's magnetic oddities seemed to foreshadow larger trends. The SAA itself has been growing and shifting westward for decades, fueling speculation that it may be tied to a potential geomagnetic pole reversal in the distant future. The 2025 proton drop, however, suggested something more immediate, a link between solar variability, interstellar dust, and Earth's most fragile magnetic zone. To some geophysicists, it looked like the SAA was acting as a sensor, picking up on disturbances in the sun's behavior long before traditional models caught them. Then came the speculation about cycles, larger than the familiar 11-year heartbeat of solar activity. The decline in proton counts was interpreted by a handful of researchers as a marker that the Gleisberg cycle, a longer 80 to 100-year modulation of solar activity, might be ending its weaker phase. If true, then Solar Cycle 25's surprises were not isolated quirks, but part of a larger resurgence in solar intensity. The SAA proton drop, in this view, was not just a local anomaly, but a bellwether, signaling that the quiet centuries of subdued solar output were closing and a more turbulent age of solar storms was dawning. Of course, not everyone agreed. Some argued that the data could be a calibration error or a temporary redistribution of particles in Earth's Van Allen belts, but cross-checks from multiple satellites, including older instruments long accustomed to the anomaly, confirmed the trend. Proton fluxes were genuinely lower than expected. Something in the Earth-Sun connection had shifted. The timing was, once again, impossible to ignore. As 3 Atlas crossed the ecliptic, as the sun's magnetic field twisted, as auroras spilled into skies unaccustomed to their glow, the South Atlantic anomaly grew quieter. One region of Earth's shield, usually noisy with proton bombardment, fell silent. For those attuned to patterns, it was like hearing an orchestra strike an offbeat note. Coincidence, perhaps. But also a pattern. 3 anomalies, 3 alignments, 3 mysteries layered atop one another. For satellite engineers, the proton drop was a welcome relief. Fewer radiation strikes meant fewer glitches, fewer corrupted data packets, fewer system resets. But relief gave way to unease as the implications sank in. If the proton flux could fall unexpectedly, it could just as easily surge without warning. Predictability was the key to survival in orbit, and predictability was slipping through their fingers. Some voices in the forecasting community began to wonder aloud if 3 Atlas had seeded the magnetosphere with dust fine enough to alter particle flows. Microscopic grains, ionized by sunlight, could in theory interact with Earth's radiation belts, changing the way protons were stored and released. No one could prove this, but the idea lingered, if only because every other explanation seemed inadequate. Meanwhile, geophysicists studying Earth's core joined the debate. The SAA is rooted in the churning of molten iron beneath our feet, where magnetic fields are generated. Could the proton decline be tied not only to solar influences, but to shifts in Earth's own dynamo? Some propose that the core was already undergoing changes, and that the solar anomalies had merely amplified or revealed them. If so, then the SAA's behavior was a warning not just about space weather, but about our planet's interior. The public, as usual, heard little of the proton drop. It lacked the drama of auroras or the spectacle of solar flares. But within the scientific community, it became one of the most puzzling anomalies of 2025. Conferences buzzed with quiet papers presenting partial explanations, each more speculative than the last. Some dared to link it to long-term cycles of solar behavior, others to transient dust-plasma interactions, still others to the deep mysteries of Earth's core. None could claim certainty. What struck many most forcefully was the direction of change. We expect anomalies to mean more storms, more particles, more chaos. Here, the anomaly was less proton bombardment, less noise, less radiation in a place that normally thrums with it. The silence of the SAA in 2025 was eerie, like the sudden stillness before a storm. Was it a pause before greater activity, or the first note of a deeper transition in Earth's interaction with the sun? Those who believe in patterns could not help but connect dots. A green interstellar visitor crossing the plane of planets. A sun twisting its magnetic architecture in ways not modeled. Auroras surging across continents. And far below, in the heart of Earth's magnetic defenses, a sudden quieting of protons. Each event alone could be explained away. Together, they formed a tapestry of anomalies too sharp to ignore. If the proton drop does indeed herald the end of the Gleisberg minimum, then the decades ahead could bring stronger solar cycles than any we have recorded in living memory. That possibility casts a long shadow over modern civilization. Satellites, power grids, internet infrastructure, all are vulnerable to the sun's moods. A quiet SAA may be the first whisper of storms yet to come. In the end, the South Atlantic anomaly's proton drop remains an enigma. Was it a fluke of particle dynamics? A local quirk in Earth's field? Was it the first measurable sign of a solar resurgence tied to deeper cycles? Or was it part of the strange synchronicity that unfolded as 3 Atlas drifted across our skies, leaving behind a trail of mysteries? Whatever the truth, the SAA has added its voice to the chorus of anomalies that marked 2025. A voice not of noise, but of silence, not of storms, but of calm. And in that calm, perhaps the promise of even greater upheavals to come. It is a reminder that the sun, the earth, and interstellar visitors are linked in ways we barely grasp, and that sometimes the loudest message comes not from what surges, but from what suddenly falls quiet. Cycle 25, Overshoot. Every 11 years, The sun rises and falls in rhythm with its magnetic cycle. Sunspots bloom, flare activity surges, and the star's field flips polarity before subsiding into relative calm. For more than a century, scientists have tracked these solar cycles with painstaking detail, charting patterns and building models to predict what comes next. Solar Cycle 25, which began in late 2019, was forecast to be a relatively modest one, comparable to or weaker than Cycle 24. The consensus was clear: humanity could expect a quieter sun with manageable storms and fewer surprises. By mid-2025, that forecast had collapsed. Sunspot counts overshot predictions, flares erupted with greater frequency, and auroras swept across skies in latitudes that had not seen them in generations. Cycle 25 was no quiet cycle. It was burning hotter, brighter, and more erratically than anyone had dared to predict. The overshoot wasn't subtle, it was stark, and it left scientists scrambling to explain why the sun had abandoned its script. The overshoot became undeniable in the data. By June 2025, sunspot numbers were nearly double the NOAA forecast, tracking at levels not seen since the early 2000s. Solar radio flux, another key marker of activity, surged in tandem. Each measure that was supposed to slope gently toward a moderate peak instead spiked into territory reserved for much stronger cycles. The predictions that had guided forecasters, infrastructure planners, and satellite operators were suddenly useless. It wasn't just numbers on a chart. The sun was acting out. X-class flares, the most powerful category, erupted in clusters, sending shockwaves across the heliosphere. CMEs followed like artillery fire, slamming into Earth's magnetosphere and triggering geomagnetic storms that rippled through technology. GPS systems faltered. Airlines were forced to reroute flights away from polar regions where radiation exposure soared. Satellites slipped into safe modes. Even amateur radio operators, long accustomed to solar interference, marveled at the intensity of the storms. Cycle 25 had broken the mold, and the evidence lit the sky in crimson and green. What made the overshoot more alarming was its timing. The sun's magnetic field twist coincided with the heightened activity, amplifying the unpredictability. Forecast models depend on relatively stable magnetic architectures. When that scaffolding shifted, the forecasts didn't just wobble, they collapsed. Predictions issued in early June, calling for mild geomagnetic conditions, were rendered obsolete within days as the sun unleashed surges that no model anticipated. It wasn't just an overshoot, it was a breakdown of trust in the very systems meant to anticipate solar behavior. To scientists, the question became urgent. Why was Cycle 25 so much stronger than predicted? One theory pointed to the sun's polar fields, the seeds of each new cycle. Data from the declining years of Cycle 24 suggested relatively weak polar magnetism, which historically correlates with weaker cycles to come. But perhaps those measurements had missed hidden reservoirs of magnetic flux beneath the surface, waiting to erupt. Another possibility was that the sun had entered a broader modulation tied to the long Gleisberg cycle of 80 to 100 years. If so, then Cycle 25's overshoot could be the opening act of a century of heightened activity. The overshoot had immediate consequences for Earth. In July 2025, auroras spilled across skies in regions that had not seen them in living memory: New Mexico, Italy, Japan. Social media filled with images of emerald curtains shimmering above city skylines, surreal reminders of the sun's power. For many, it was a moment of wonder. For forecasters and engineers, it was a warning. If the sun could produce auroras this widespread during what was supposed to be a moderate cycle, what might it do at the peak? Satellites bore the brunt. Operators reported anomalies across constellations: communication delays, navigation drift, power surges in circuits. Starlink satellites in particular faced increased drag as solar activity heated Earth's upper atmosphere, expanding it and pulling low-orbiting craft downward. In 2022, a similar surge had destroyed dozens of Starlink units. By 2025, companies had adapted, but the overshoot still strained their defenses. Engineers knew that one unanticipated storm could wipe out millions of dollars in hardware. The overshoot also posed risks for terrestrial infrastructure. Power grid managers in North America and Europe began running emergency drills more frequently, bracing for geomagnetically induced currents that could overload transformers. The specter of the 1989 Quebec blackout, caused by a geomagnetic storm, hung over every new surge. Cycle 25 was proving itself capable of storms on that scale, if not larger. The overshoot meant the probability curve had shifted. What was once low risk was now possible. But the overshoot wasn't merely about risk. For scientists, it was also an opportunity. Every anomaly is a window into deeper understanding. Cycle 25's unexpected strength revealed that our models of the solar dynamo, the processes churning deep in the sun's interior, remain incomplete. Helioseismology, the study of solar vibrations, hinted at turbulence deeper than expected. Some researchers proposed that layers of magnetic flux were stacking and reconnecting in ways not yet incorporated into simulations. If so, then overshoots might not be flukes, but features, emerging whenever hidden reservoirs of magnetism rise to the surface. Speculation, of course, thrives when models fail. Some voices outside the mainstream argued that external influences, galactic magnetic fields, interstellar dust streams, even interstellar objects like 3I Atlas, could be amplifying the sun's volatility. Most scientists reject the idea of direct causation. The sun is simply too massive, too self-contained for a comet to alter its cycles. Yet the timing of 3I Atlas's ecliptic crossing, the magnetic twist, and the overshoot was difficult to ignore. At the very least, the alignment became a symbol of how little we truly know about the interplay of cosmic events. The overshoot also revived historical comparisons. During the Maunder Minimum in the 17th century, solar activity nearly vanished, plunging Europe into the coldest stretch of the Little Ice Age. Conversely, during the modern maximum of the mid-20th century, solar activity surged to heights unseen in centuries, possibly influencing climate and technology alike. If Cycle 25 was overshooting predictions, some wondered whether humanity stood on the threshold of another maximum, a century of heightened storms and radiant skies. For those who look for patterns, Cycle 25's overshoot was part of a trilogy: the anomalous brightness of 3I Atlas, the sun's magnetic twist, and the proton drop in the South Atlantic anomaly. Together, they suggested not randomness but rhythm, a hidden beat in the machinery of the cosmos. Whether that rhythm was real or imagined, its psychological effect was undeniable. People began to see connections where before they had seen isolated events. The sun's overshoot was no longer just an astrophysical puzzle, it was a piece in a narrative of synchronicity. The overshoot carries practical implications for the years ahead. If Cycle 25 is this strong already, then the peak could deliver storms rivaling the Carrington event of 1859. That storm set telegraph wires ablaze and electrified the sky. A Carrington-level event today would cripple satellites, disrupt global communications, and potentially collapse power grids. The overshoot makes that scenario less a matter of if and more a question of when. Yet overshoot also carries a paradoxical beauty. While forecasters fretted and engineers braced for failures, ordinary people marveled at auroras dancing where none had before. In cities where light pollution usually hides the heavens, the sky briefly tore open to reveal the sun's handiwork, spilling color into lives otherwise disconnected from the cosmos. In that sense, the overshoot was both danger and gift, a reminder of our fragility and of the wonder still capable of breaking through the modern world's noise. Cycle 25 is far from over, but its overshoot has already rewritten the story of solar forecasting, exposing weaknesses in models, revealing strengths in the sun we had underestimated, and hinting at larger cycles still unfolding beyond our comprehension. Whether it marks the dawn of a new solar maximum or just a temporary flare of unpredictability, it has ensured that Cycle 25 will be remembered not as a quiet passage, but as a warning that the sun does not answer to our predictions. In the end, the overshoot is less about numbers than about humility. We thought we could chart the heartbeat of our star, compress its rhythms into graphs and forecasts. But the sun has reminded us in plasma and fire that it still holds mysteries we cannot yet grasp. And in that reminder, delivered in the form of Cycle 25's blazing overshoot, lies both our vulnerability and our ongoing quest to understand the forces that shape life under its light. Hidden influences. Every great mystery carries with it a shadow, the sense that what we see on the surface is only part of the story, and that unseen forces may be shaping the outcome from behind the curtain. When it comes to the sudden magnetic twist of the sun and the overshoot of solar cycle 25, This shadow looms large. Astronomers can chart the visible, measure the plasma, and model the cycles, but there remains the nagging suspicion that hidden influences, subtle, elusive, and perhaps interstellar in origin, may be playing a role. The first place to look for hidden influences is the dust and plasma environment that the sun constantly moves through. Our solar system is not an island, but a ship sailing through the interstellar medium. Clouds of dust, magnetic fields from the galaxy, and streams of charged particles all buffet the heliosphere. When 3I Atlas entered the Ecliptic in 2025, it was not just a single body passing by. It carried with it a vast cloud of dust, a coma swollen with particles ionized by sunlight. Those grains interacted with solar wind, scattering photons and altering currents in ways not yet fully understood. Could such a halo of alien dust have seeded instabilities in the solar wind at the exact moment the sun's field twisted? The possibility cannot be dismissed outright, even if proof remains elusive. Another hidden influence lies in the sun's interior itself. The solar dynamo, buried deep in the convective zone, is the true engine of the sun's magnetic behavior. Our models, based on helioseismology and long-term observations, suggest patterns of how magnetic fields are generated and rise to the surface. Yet the overshoot of cycle 25 makes clear that something in those models is incomplete. Perhaps magnetic flux ropes, twisted and stored for decades, were released unexpectedly. Perhaps unseen reservoirs of magnetism trapped in the tachocline surfaced in ways we cannot yet predict. The sun may hold secrets in its depths that appear from our limited vantage point as sudden anomalies. But speculation stretches further. Some researchers quietly wonder whether interstellar magnetic fields, those threading through the galaxy itself, might interact with the sun more strongly than assumed. The heliosphere is shaped not only by solar outflow, but by the galactic magnetic environment into which it expands. If those fields fluctuate, or if the sun drifts into a denser or more magnetized region of space, its magnetic cycles could be nudged off course. The entry of 3 Atlas, aligned so perfectly with the ecliptic, might be more than coincidence. It could be a messenger, arriving along currents shaped by the galaxy's invisible scaffolding. There is also the question of resonance. Nature often hides its influence not in direct force, but in timing. Small nudges, if applied at the right moment, can amplify into great effects. Could 3I Atlas have been such a nudge? Its mass is trivial compared to the sun's, but its timing, crossing the planetary plane just as the sun's magnetic fields reoriented, was uncanny. Some propose that interstellar bodies trailing streams of dust and gas may act as triggers, setting off resonances in plasma flows that were already unstable. If true, then the influence of visitors like 3I Atlas is not in brute force, but in the precision of their arrival. Historical echoes add weight to the speculation. Ancient chronicles often describe comets appearing in skies during years of strange weather, unusual auroras, or solar obscurations. Modern science dismisses most of these as coincidence or embellishment. Yet when Cycle 25's anomalies align so closely with the path of an interstellar wanderer, the parallels are difficult to ignore. Were those past observers witnessing hidden influences similar to what we see now? Comets arriving not as causes, but as heralds of deeper changes unfolding in solar behavior? One of the most provocative hidden influences is the galactic tide of cosmic rays. These high-energy particles, accelerated by distant supernovae and galactic fields, constantly rain upon the solar system. Normally, the sun's magnetic field modulates their intensity, deflecting them when the field is strong and allowing more to pass through during quiet phases. But if Cycle 25's overshoot was amplified by changes in cosmic ray flux, then the hidden influence might not be 3I Atlas at all, but the galaxy itself pressing upon the heliosphere. Data from neutron monitors on Earth suggested unusual cosmic ray patterns in early 2025, adding yet another puzzle piece to the mosaic of anomalies. Closer to home, Earth's own magnetic oddities may also be part of the story. The South Atlantic anomaly, already growing and shifting, experienced its proton drop in the same window as the solar twist. Some geophysicists argue that Earth's field is weakening in ways that make it more sensitive to solar variations. In this view, the hidden influence is not external at all, but internal, our planet's magnetism exposing us more fully to the sun's moods. If Earth's shield is faltering, then every solar overshoot will feel amplified, and every interstellar coincidence will appear more dramatic than it truly is. The danger of hidden influences is that they cannot be modeled easily. Forecasting thrives on measurable inputs: sunspot counts, magnetograms, flare indices. Hidden factors, dust grains, galactic tides, interstellar visitors, are harder to quantify, and yet they may be shaping the very anomalies that models struggle to predict. The overshoot of Cycle 25 is a reminder that science is not just about what we can measure, but about what we might be missing. Speculation does not stop at physics. Some voices, far outside the mainstream, whisper about engineered influences. The idea that anomalies like 3I Atlas may not be purely natural. The brightness, the polarization mystery, the timing with solar shifts, to some, these resemble signals more than accidents. Was the object a fragment of technology, a probe designed to interact with stellar fields? Most scientists reject this outright, preferring natural explanations. Yet the persistence of the question itself shows how unsettling hidden influences can be. When coincidences stack too high, imagination seeks intent. Whether natural or imagined, the sense of influence is undeniable. Something nudged Cycle 25 beyond its predicted limits. Something aligned with 3 Atlas's passage to create a narrative of timing too sharp to ignore. Perhaps the influence lies in dust grains we cannot yet measure, or in magnetic fields we cannot yet map. Perhaps it lies in the sun's hidden interior, storing power we underestimate. Or perhaps it lies in our own minds, wired to see patterns in the chaos of the cosmos. But one thing is certain: hidden influences matter. They shape how we interpret anomalies, how we refine models, how we prepare for the storms to come. To deny them is to accept blindness. To seek them is to push deeper into the unknown. The story of 2025 is not just one of visible auroras and measurable flares. It is also the story of what we suspect but cannot prove, of whispers in the data, of shadows cast by visitors from beyond the stars. In the end, the lesson of hidden influences is humility. The sun, the Earth, and the galaxy weave together in ways we are only beginning to trace. 3 Atlas's timing may be coincidence, or it may be resonance. Cycle 25's overshoot may be a quirk of magnetism, or a symptom of deeper tides. The truth remains hidden for now. But the very act of searching for these influences ensures that when the next interstellar wanderer arrives, and the sun again defies prediction, we will be better prepared to recognize the unseen forces shaping the drama above. Because the greatest mysteries are not always in what we can see, but in the hidden currents moving silently beneath the surface, guiding events toward moments too extraordinary to call chance. Stealth CMEs and magnetic surprises. Solar storms are among the most dramatic spectacles in astrophysics, but they usually announce themselves. When a coronal mass ejection, the violent expulsion of billions of tons of plasma from the sun, erupts, the surface often betrays its fury with flares, filament lifts, or sudden bright arcs across the corona. These signals give forecasters time to prepare, warning satellites, grid operators, and astronauts that a storm is inbound. But every so often, the sun plays a more subtle game. It releases energy without warning, ejecting plasma in silence. These are the stealth CMEs, and they are among the most unsettling magnetic surprises in solar science. In July 2025, as 3I Atlas glided across the ecliptic and the sun's magnetic field twisted, stealth events were everywhere. Auroras swept across skies far from the poles, satellites flickered in and out of safe modes, and geomagnetic currents crept through Earth's crust. Yet when forecasters looked for the obvious culprits, explosive flares or visible eruptions, they found none. Instead, coronagraph images revealed faint, ghost-like arcs of plasma, emerging almost invisibly and racing outward into space. These were not ordinary CMEs. They were stealth events, barely perceptible until their effects reached Earth. What makes stealth CMEs so dangerous is their lack of clear origin. Unlike traditional eruptions, they often lack the hot, bright signatures of flares. Instead, they seem to seep from the corona, driven by subtle magnetic rearrangements that escape notice. For forecasters, they are a nightmare. Without surface signals, predictions are nearly impossible. By the time satellites detect a stealth CME in interplanetary space, it may be only hours from impact. That means civilization's defense window shrinks from days to minutes. In 2025, Stealth events piled one atop another, confusing even the most seasoned experts. Some were faint arcs slipping unnoticed across coronagraph fields until data review days later. Others masqueraded as harmless, slow-moving plasma until they slammed into Earth's magnetosphere with unexpected force. This unpredictability led to cascading disruptions. Communications blackouts hit military satellites. Surveyed auroras reached latitudes not seen in decades. Amateur radio operators reported bizarre propagation patterns, with signals skipping in strange arcs around the globe. It was as though the sun had begun to breathe invisibly, expelling magnetic storms that played hide-and-seek with our instruments. The coincidence with 3I Atlas's crossing only deepened the mystery. Could the vast dust cloud around the interstellar body have interacted with solar plasma, creating conditions for stealth eruptions? Could alien particles in the heliosphere have weakened coronal structures, making them more prone to collapse without visible flare triggers? Mainstream science offered no consensus, but the alignment of events left the question lingering. When coincidence stacks too neatly, suspicion grows. The magnetic surprises weren't limited to stealth CMEs. The sun's field itself seemed unstable, flickering between configurations as though struggling to find equilibrium. Instruments recorded rapid shifts in polarity, small but significant enough to alter solar wind paths. Earth felt the effects immediately. The magnetosphere pulsed erratically, compressing then rebounding as streams of plasma struck from unpredictable directions. The usual Parker spiral, the elegant arc of solar wind shaped by the sun's rotation, looked jagged and distorted in data visualizations. For those monitoring space weather, it was like watching a compass needle spin in circles. One particularly puzzling event unfolded in early July, when Earth's magnetometers registered a sharp storm with almost no warning. Data from coronagraphs showed only a faint, diffuse CME hours earlier, so faint that most analysts had dismissed it as insignificant. Yet, when its plasma cloud reached Earth, it carried with it a magnetic field oriented southward, the most geo-effective orientation, one that couples strongly with Earth's northward pointing field. The result was a geomagnetic storm out of proportion to the CME's apparent size. Forecasters were forced to admit what they dreaded. Stealth events can be as disruptive as the most violent, visible storms. This unpredictability created a growing sense of unease. Our civilization relies on foreknowledge. Power grids must prepare for geomagnetically induced currents. Airlines need radiation forecasts to reroute flights. Satellites require warning to switch into protective modes. But stealth CMEs rob us of that cushion. By the time they are detected, their plasma is often already upon us. For the first time in years, space weather agencies issued bulletins filled not with confident predictions, but with cautionary vagueness. Unmodeled disturbances likely. For the public, it was jargon. For those in the field, it was a confession of ignorance. The surprises also challenged long-standing assumptions about solar physics. Why do stealth CMEs occur at all? The leading hypothesis is that they emerge from the quiet sun, areas lacking strong sunspots or active regions. Instead of explosive reconnection events, they may result from gradual destabilizations of coronal streamers, magnetic arches that stretch outward and collapse silently. These collapses release plasma, but without the fireworks of flares. If true, then stealth events are not rare outliers, but intrinsic features of solar behavior, overlooked simply because they are so hard to detect. In 2025, the frequency of these events seemed to spike. Some link this to Cycle 25's overshoot, arguing that heightened magnetic flux made the sun more prone to subtle instabilities. Others suggested that our instruments, more sensitive than ever, were finally catching what had always been there. Yet the coincidence with the interstellar visitor kept resurfacing. 3 Atlas was dustier than expected, glowing brighter than models allowed, and scattering exotic particles into space. If those particles reached the sun, even in trace amounts, could they have altered coronal conductivity just enough to tip streamers into collapse? The idea remains speculative, but it underscores how fragile the boundary is between known physics and unanswered questions. Historical parallels add context. In 2012, a massive stealth-like CME narrowly missed Earth, passing through our orbital path days before our planet arrived. Had it struck, it could have caused damage on the scale of the 1859 Carrington event. That near miss has haunted space weather research ever since. Now, in 2025, with stealth events striking repeatedly, the fear returned. Was Cycle 25 priming Earth for another Carrington-level disaster, hidden behind eruptions too faint to track until too late? The magnetic surprises extended even to other planets. Mars, already stripped of its global magnetic shield, experienced direct hits from stealth CME plasma. Orbiters detected sharp increases in atmospheric loss as hydrogen and oxygen ions streamed into space. For a planet already struggling to hold on to its atmosphere, the impact was sobering. Jupiter's magnetosphere, by contrast, lit up with auroras of its own, bright bursts recorded by the Juno spacecraft. The sun's surprises, it seemed, were written across the entire solar system. For Earth, the takeaway was both unsettling and humbling. Stealth CMEs reminded us that the sun does not always announce its intentions. The models we trust can fail when events unfold in silence. The forecasts we rely on can collapse under the weight of unpredictability. And in the backdrop, 3I Atlas drifted through the ecliptic, its timing uncanny, its presence impossible to ignore. Whether or not it had any influence, it became part of the narrative, an interstellar witness to a season of solar surprises. In the aftermath, scientists began pushing for new approaches. Better coronagraphs, more sensitive to faint plasma arcs, wider networks of heliophysics satellites positioned at multiple longitudes to catch stealth events from different angles. Machine learning algorithms trained not just on obvious eruptions, but on the quiet, subtle signatures of collapsing streamers. The goal was simple: to catch the invisible before it becomes unstoppable. But beyond the practical, the story of stealth CMEs carries a philosophical weight. It is a reminder that the sun, so familiar and so studied, remains a frontier of mystery. We orbit a star we do not yet fully understand. Its storms, whether loud or silent, remind us of our fragility, our dependence on forecasts, and our vulnerability to surprises. Stealth CMEs are the solar equivalent of whispers that carry the force of shouts. In 2025, they became the punctuation marks of a season already defined by anomalies: a sun twisting its fields, a cycle overshooting predictions, and an interstellar visitor crossing the ecliptic. The surprises will be debated for years, but one truth is already clear: we must learn to expect the unexpected, because sometimes the most dangerous storms are the ones that arrive without warning. Timing patterns and synchronicity. In science, timing is often treated as coincidence unless proven otherwise. But when patterns repeat, when multiple events unfold in unnerving alignment, the line between coincidence and synchronicity begins to blur. That is exactly what happened in mid-2025. The sun's magnetic field twisted, stealth CMEs surged, proton fluxes in the South Atlantic anomaly dropped, and auroras spilled across unexpected skies, all in the very window that the interstellar visitor 3I Atlas slipped across the ecliptic. Alone, each anomaly can be explained. The sun is volatile, proton levels fluctuate, comets arrive on hyperbolic paths, but together, the simultaneity demanded attention. Astronomers are trained to search for causation, to strip chance from signal, yet the sheer convergence of these events felt like a narrative being written in real time, a cosmic script whose timing was too sharp to ignore. The first pattern was temporal clustering. From late June into mid-July 2025, anomalies stacked one atop another. The solar magnetic twist occurred within hours of 3I Atlas's crossing. The stealth CMEs arrived in waves, not isolated bursts. The proton drop in the South Atlantic anomaly unfolded almost simultaneously, and auroral records spiked in regions as far apart as Europe, South America, and Asia. In data terms, this was a cluster, an unusual concentration of rare events in a narrow window. Statistically, clustering of independent phenomena is improbable, which raises the question: were they truly independent? The second pattern was geometric alignment. 3I Atlas's orbit was not random, but nearly flush with the ecliptic, the plane where solar wind structures, planetary orbits, and the heliospheric current sheet all interweave. By crossing this plane, the interstellar body intersected the very architecture of solar magnetism at the exact moment that architecture convulsed. Geometry, timing, and anomaly aligned, creating a synchronicity too striking to dismiss as background noise. Some scientists dismissed the significance outright. Correlation is not causation, repeating the mantra of rational analysis. But others admitted unease. Science progresses not only through hard evidence, but also through curiosity triggered by coincidence. When multiple anomalies overlap, it is natural to ask whether they share a hidden driver. The sun's interior, the galaxy's magnetic tides, or perhaps, more provocatively, the influence of interstellar material brushing against solar plasma. The third pattern was historical echo. Ancient records from China, Babylon, and Europe describe comets appearing alongside strange celestial phenomena, unseasonable auroras, darkened suns, or unusual weather. Historians usually chalk these up to superstition, a tendency to connect unrelated events. But in 2025, as anomalies clustered around 3I Atlas, those ancient chronicles seemed less like fantasy and more like precedent. Could humanity have witnessed synchronicities like this before, only without the instruments to measure them? Beyond patterns in space and time, there was a psychological layer. Humans are hardwired for pattern recognition. It is how our ancestors survived, by noticing alignments that suggested danger or opportunity. That wiring has not faded. In the anomalies of 2025, pattern-seeking minds saw synchronicity, a deeper rhythm beneath the surface chaos. The rational resisted, yet the emotional and intuitive pressed forward. This cannot all be random. One of the most haunting aspects of the timing was its resonance with Solar Cycle 25's overshoot. Predictions had promised a modest peak. Instead, sunspot counts, flare activity, and auroral frequency all surged far beyond expectations. This overshoot was not confined to July. It stretched across the cycle. Yet the sharpest anomalies clustered around 3I Atlas's crossing, as though the cycle's excess had chosen that moment to make itself most visible. Was it coincidence, or was the comet's arrival a cosmic metronome, marking a beat already set in motion? Some theorists pushed further, suggesting resonant amplification. In physics, small triggers can magnify large systems when they arrive at the right frequency. Could the dust halo of 3I Atlas, ionized by sunlight, have brushed against plasma instabilities just as the sun's magnetic field was poised to twist? Even if the mass of the comet was trivial, the timing of its crossing could have amplified pre-existing turbulence. Like a perfectly placed tap on a resonant bell, the effect would not lie in force, but in precision. The concept of synchronicity was first popularized by psychologist Carl Jung, who described it as meaningful coincidence, alignments that feel connected without obvious causation. In the story of 2025, synchronicity seemed almost scripted. A visitor from the stars arrives, the sun twists, Earth's magnetosphere shudders, proton counts fall, auroras spread. One could dismiss it all as coincidence, yet the narrative carried weight. It was not just random noise, it was a story unfolding with chapters written in plasma and dust. Patterns also emerged in the scales of response. Local anomalies, the South Atlantic proton drop, occurred simultaneously with global disturbances, auroras across continents, and solar system-wide phenomena, magnetic shifts felt as far as Mars and Jupiter. The synchronicity spans scales from Earth's core to the heliosphere. That breadth made it harder to dismiss. Multiple systems, planetary, stellar, interstellar, all seemed to vibrate in harmony for a brief window of time. Skeptics offered natural explanations. The sun is chaotic. Clustering is inevitable in long enough datasets. Interstellar visitors are common, though rarely detected. Proton levels fluctuate, but even skeptics admitted the statistical weight of the clustering was unusual. What are the odds that so many anomalies across so many scales would align so neatly? Chance is possible, but unlikely. For those attuned to myth and symbolism, the synchronicity was even richer. A green comet crossing the planetary plane just as the sun twisted its magnetism was almost archetypal, echoing stories of sky serpents and cosmic messengers found in cultures worldwide. In myth, timing is never coincidence, it is destiny. The modern mind may resist such framing, but the resonance lingers. Science measures events, stories give them meaning. In 2025, the two collided. The deeper question is what synchronicity demands of us. Do we dismiss it, satisfied with coincidence? Or do we treat it as a signal to search harder for hidden connections? History shows that anomalies often precede breakthroughs. The orbit of Uranus once wobbled inexplicably until Neptune was discovered. Mercury's perihelion shift defied Newton until Einstein revealed relativity. Perhaps Cycle 25's anomalies, synchronized with 3I Atlas, are another wobble in the fabric of science, a riddle that will force us to expand our understanding. If hidden forces exist, galactic fields, interstellar dust interactions, long solar modulations, they will only be revealed by following the thread of synchronicity. Ignoring it risks overlooking discoveries waiting just beyond the horizon of our models. Treating timing as meaningless may blind us to timing as clue. As 3I Atlas faded from view, the memory of its uncanny timing lingered. The sun continued to flare, auroras ebbed and flowed, proton counts returned to normal. The anomalies subsided, but the pattern they formed remained etched into the narrative of Cycle 25. Scientists will debate it for years. Coincidence or connection, noise or signal. But for those who lived through it, who watched green auroras spill into unexpected skies while a green interstellar body traced the ecliptic, it felt like more than chance. It felt like the cosmos had whispered, synchronizing events across scales, hinting that the universe is not as random as we tell ourselves. In the end, timing patterns and synchronicity force us into humility. They remind us that science is not just about what we can measure, but also about what we choose to notice. The alignment of 2025 may prove to be coincidence, but even coincidence can be a compass, pointing us toward questions we did not know to ask. And sometimes, in the mysteries of timing, the universe reveals its deepest truths, not in what happens, but in when it happens. Implications and open questions. When the dust of mid-2025 settles in the historical record, the events surrounding 3I Atlas and the sun's magnetic contortions will not simply be remembered as curiosities. They will linger because they cut at the heart of two essential truths. We do not fully understand our star, and we do not yet know how to interpret interstellar visitors. The synchronicity of these anomalies forces us to consider not only what happened, but what it might mean for the future of space weather, planetary defense, and our place in a much larger cosmic environment. The most immediate implication lies in the limits of forecasting. Space weather predictions failed spectacularly during the July surges, leaving airlines, satellite operators, and grid managers exposed. The reliance on models that assume solar cycles are neat, predictable curves has now been shattered. If Cycle 25 could overshoot this dramatically, then the foundation of our predictive architecture must be re-examined. For those who depend on warnings, farmers relying on GPS, pilots calculating routes, military satellites monitoring communication networks, the unsettling message is that the sun can and will surprise us, often when we least expect it. Closely tied to this is the vulnerability of modern civilization. The Carrington event of 1859 devastated telegraph systems, but humanity was largely insulated by its lack of dependence on electronics. Today, a storm of similar magnitude, or even a stealth CME arriving unnoticed, could cripple the global internet, collapse power grids, disable satellites, and set economies back decades. The implication of Cycle 25's overshoot is clear. Our infrastructure is fragile in ways we barely acknowledge, and our margin of safety may be far narrower than policymakers assume. Another implication extends beyond Earth to the habitability of other planets. Mars, pummeled by stealth CMEs and stripped further of its tenuous atmosphere, reminded us that any future colony there will be at the mercy of solar moods. A strong enough cycle could undo decades of terraforming progress in a matter of weeks. Even Jupiter's magnetosphere lit up with auroras of its own, showing that the sun's anomalies ripple across the entire solar system. The implication is sobering. Solar variability is not just an earthly inconvenience, but a galactic constant that shapes planetary destinies. There are also scientific implications for our models of the solar dynamo. The sun's magnetic twist, the proton drop in the South Atlantic anomaly, and the stealth CME surge all point to gaps in our understanding of how magnetic energy builds, releases, and propagates. If our models cannot capture these events, then our picture of the solar interior remains dangerously incomplete. Open questions proliferate. Were hidden flux reservoirs unleashed? Did the sun encounter a change in the interstellar medium? Or were we simply unlucky witnesses to a rare but natural coincidence? Each answer carries weight because each forces us to reshape the way we understand stellar behavior. And then there are the interstellar implications. 3I Atlas is only the third interstellar object ever observed, following Oumuamua and Borisov. Its passage during such a turbulent solar episode invites uncomfortable questions. Are these visitors more common than we realize, and could they sometimes coincide with solar disturbances? Do they carry with them unique dust or plasma environments capable of interacting with solar fields in subtle ways? Or are they simply messengers, their arrival aligning with larger galactic cycles we have yet to recognize? We know the Sun orbits the Milky Way every 225 million years, passing through different regions of magnetic density and interstellar gas. Perhaps visitors like 3I Atlas are the visible tip of much larger interactions between our star and its galactic neighborhood. The question of hidden influences remains tantalizing. Could interstellar dust act as a trigger for solar instabilities, seeding turbulence at just the right moment? Could cosmic rays, modulated by the galaxy's magnetic field, have primed Cycle 25 for overshoot? These questions remain unresolved, but their implications are profound. If the Sun is more porous to external influence than we thought, then the neat separation between internal stellar processes and external galactic environments dissolves. We may need to think of the Sun not as an isolated engine, but as an instrument playing in a cosmic orchestra. Another open question revolves around long cycles. The Gleisberg cycle, spanning 80 to 100 years, has long been suspected of modulating the strength of solar activity. If Cycle 25 marks the beginning of a renewed period of solar intensity, then the implications extend for decades. Are we entering a new modern maximum, a century of heightened auroras, stronger storms, and more dangerous space weather? Or was this merely a local overshoot destined to fade as quickly as it appeared? The truth may not be known until Cycle 26 or 27 unfolds, leaving us to wait in uncertainty. There are also geophysical implications for Earth. The proton drop in the South Atlantic anomaly was not just a quirk, it may be part of a larger trend. Earth's magnetic field has been weakening for over a century, and the anomaly is drifting westward and splitting into two lobes. Some geophysicists warn this could be the prelude to a pole reversal. If so, then the timing of the drop during solar chaos is doubly concerning. Was it merely bad luck, or was Earth's weakened shield resonating with solar instabilities? If our planet is indeed moving toward a magnetic reversal, then our vulnerability to solar storms could multiply dramatically in the centuries ahead. The open questions do not end with science, they extend into philosophy and meaning. Humans cannot help but notice patterns. When an interstellar wanderer crosses the planetary plane at the same moment, the Sun twists its magnetism and Earth's shields weaken, it feels like synchronicity. Science may ultimately prove it coincidence, but the implication for culture is that we may begin to see comets and cosmic events as messengers once again, not in the superstitious sense of omens, but in the Jungian sense of meaningful coincidence, reminders that the universe often whispers in the language of timing. Another implication lies in preparedness. The events of 2025 will likely accelerate investment in new satellites, better coronagraphs, and machine learning models to detect stealth CMEs before they arrive. Governments and corporations may be forced to rethink their reliance on fragile space infrastructure. The open question is whether humanity will take these warnings seriously or dismiss them until a catastrophic storm forces action. Perhaps the most profound open question is this: are we witnessing a larger cosmic pattern? The past decade has seen not just 3I Atlas, but a rising drumbeat of interstellar discoveries, from rogue planets to mysterious fast radio bursts. If solar anomalies, planetary vulnerabilities, and interstellar visits align more frequently in the future, will we still call it coincidence? Or will we begin to admit that our star, our solar system, and the galaxy itself may be entangled in ways our current physics cannot yet explain? In the end, the implications and open questions left by the events of 2025 may matter less for their immediate answers than for the humility they inspire. We thought we understood solar cycles, but we did not. We thought we could predict storms, but stealth CMEs humbled us. We thought interstellar comets were rare, but two have arrived in a few short years, and a third has already rewritten the rulebook. The implication is clear. The universe is more dynamic, more interconnected, and more mysterious than our models allow. And so the open questions remain. Was 3I Atlas merely a silent witness, or an active participant in the Sun's unrest? Are we entering a new century of solar turbulence or witnessing an isolated overshoot? Is Earth's magnetic field quietly preparing for upheaval, amplifying our vulnerability? Or was it all coincidence? The cruel tricks of chance clustering events too close together for our minds to ignore. The answers will not come quickly, but the legacy of 2025 will be its questions, lingering in every aurora photograph, every magnetometer anomaly, every green spark in the sky. Questions that force us to admit we are still in the early chapters of understanding the star we orbit. Questions that leave us staring upward, unsettled but awed, waiting for the next interstellar visitor or the next solar surprise to show us just how much we still do not know.